Imagine looking up at the night sky, seeing countless galaxies stretching across the cosmos, and realizing that maybe, just maybe, one of them isn't made of the same stuff as everything we know. What if, out there in the universe, there's a galaxy made entirely of antimatter? Not just a few stray particles, but a massive, structured, star-filled galaxy composed of the mirror opposite of normal matter. It sounds like science fiction, but it's a real possibility, one that could completely change our understanding of the universe. For decades, scientists have debated whether antimatter galaxies could exist somewhere beyond our reach. The idea is as mind-blowing as it is controversial because, according to everything we know, matter and antimatter should have annihilated each other long ago. But the universe clearly exists. We exist. So, where did all the antimatter go? And if it's still out there, could it have formed entire galaxies, stars, and even planets? To understand this, we first have to go back to the beginning, the Big Bang. When the universe first exploded into existence, it should have created equal amounts of matter and antimatter. That's what physics tells us. But here's the mystery: for some reason, the universe is almost entirely made of matter. If there were an equal amount of antimatter, we wouldn't be here. Instead, every time matter and antimatter met, they would annihilate each other, leaving behind nothing but energy. That means something happened, something that gave matter the upper hand. But what? Some theories suggest that tiny differences in the behavior of matter and antimatter led to an imbalance, allowing matter to dominate and antimatter to mostly disappear. Others propose that antimatter didn't vanish, it just got separated. If that's true, then somewhere out there, antimatter galaxies could be floating in the cosmic darkness, hidden from us simply because we haven't found a way to detect them. Now, you might be wondering, if there were entire antimatter galaxies, wouldn't we have seen them by now? Wouldn't they be interacting with normal matter and causing massive explosions? That's a great question, and it's one of the biggest reasons why scientists are skeptical. Whenever matter and antimatter meet, they annihilate in a flash of energy, producing high-energy gamma rays. If an antimatter galaxy were colliding with regular matter in space, we'd expect to see a massive amount of gamma radiation lighting up the sky. But so far, we haven't seen anything that conclusively proves this is happening on a large scale. However, that doesn't mean antimatter galaxies are impossible. In fact, some scientists believe they could exist in isolated pockets of the universe, far away from normal matter, which would explain why we don't see constant annihilation events. If an antimatter galaxy is surrounded by an antimatter-dominated region of space, it could exist just like a normal galaxy does, with stars, planets, and maybe even life, except everything would be made of antimatter instead of matter. But here's where things get even weirder. If there were entire antimatter galaxies, what would they look like? Would they behave just like normal galaxies, with antimatter stars burning and antimatter planets orbiting? According to physics, the laws of nature should work the same way for antimatter as they do for matter. That means an antimatter star would shine just like a normal star, and an antimatter planet could theoretically support antimatter life, if such a thing is even possible. But the moment one of these antimatter objects came into contact with regular matter, it would be completely obliterated in a burst of energy. So, how would we even detect an antimatter galaxy? If normal matter and antimatter are so similar, how could we tell the difference? Scientists have a few ideas. One method involves searching for telltale signs of cosmic rays that might be coming from antimatter sources. If we can find evidence of antimatter helium or other antimatter particles that don't originate from human-made experiments, it could be a sign that large amounts of antimatter exist somewhere in the universe. Another possibility is looking at how galaxies interact with one another. If an antimatter galaxy ever collided with a normal galaxy, the result would be catastrophic, an enormous burst of gamma rays that would be unlike anything we've ever seen. Some scientists are actively scanning the universe for these kinds of signals, hoping to find the smoking gun that proves antimatter galaxies are real. But if we did find an antimatter galaxy, what would that mean for our understanding of physics? It would be one of the biggest discoveries in the history of science. It would force us to rethink how the universe was formed, how it evolved, and why matter won out over antimatter. It might even open the door to new forms of energy, new ways of exploring space, or even new possibilities for life beyond Earth. And that brings us to an even bigger question. If antimatter galaxies exist, could there be antimatter life? Could there be entire civilizations out there, made of antimatter, completely separate from us, and completely unaware that they are fundamentally different from the rest of the universe? If such a civilization existed, and they somehow came into contact with us, the results would be disastrous. The moment matter and antimatter meet, they annihilate. That means shaking hands with an antimatter alien wouldn't just be dangerous, it would be impossible. The idea of antimatter galaxies pushes the limits of what we think we know about the universe. It challenges our understanding of physics, raises new questions about the origins of everything, and forces us to consider the possibility that the universe is far stranger than we ever imagined. Could there really be an antimatter galaxy out there, hidden among the billions of galaxies we've already discovered? The truth is, we don't know. But if one does exist, it's only a matter of time before we find it. The search for an antimatter galaxy isn't just a thought experiment, it's an active area of research. Scientists have been trying to detect large-scale antimatter structures in the universe for decades, but the challenge is that antimatter behaves almost exactly like normal matter. If you were to look at an antimatter galaxy through a telescope, it would appear almost identical to a regular galaxy. Its stars would shine the same way, its planets would orbit in the same patterns, and its black holes would bend light just like any other. The only difference is that everything inside it would be made of the opposite kind of matter, meaning the moment it came into contact with our universe, it would annihilate in a burst of energy. This raises a crucial question. If an antimatter galaxy exists somewhere out there, how far away would it have to be to remain undetected? Given the vastness of the universe, it's entirely possible that antimatter galaxies could exist in regions so distant that they have never interacted with any normal matter. The observable universe is about 93 billion light-years across, but that's just what we can see. Beyond that, the cosmos could stretch infinitely. If antimatter galaxies are out there, they might be hiding in the deepest, most isolated regions of space, beyond the reach of any gamma-ray detection or cosmic ray analysis. One of the key tools scientists use to search for antimatter is the Alpha Magnetic Spectrometer, AMS-02, a particle detector attached to the International Space Station. Its job is to scan cosmic rays for signs of antimatter particles that shouldn't exist naturally. If the AMS-02 were to detect something like an antihelium nucleus, meaning a helium atom made entirely of antimatter, it would be strong evidence that antimatter exists on a large scale somewhere in the universe. So far, there have been some intriguing findings, but nothing definitive. Another potential way to detect an antimatter galaxy is through the cosmic microwave background radiation, CMB. This radiation is the afterglow of the Big Bang, and it provides a snapshot of the early universe. If large amounts of antimatter were present in the past, they might have left subtle imprints in the CMB that we could detect today. Scientists have been analyzing this radiation for any anomalies that could hint at antimatter regions, but once again, the evidence is inconclusive. But let's step away from the technical side for a moment, and imagine what an antimatter galaxy would actually be like. If you were somehow able to travel to one without being obliterated, what would you find? Assuming the laws of physics hold true, an antimatter galaxy would function just like any normal galaxy. It would have antimatter stars burning with fusion reactions, antimatter planets orbiting in stable paths, and possibly even antimatter black holes warping space-time. The strangest part? If there were antimatter life in this galaxy, it might not even realize that it's made of something different from the rest of the universe. Imagine an antimatter civilization, millions or even billions of light years away, looking up at their own night sky, wondering if they are alone in the universe. From their perspective, they might assume that everything is made of antimatter, just as we assume everything is made of matter. If they ever tried to make contact with us, they wouldn't know that their very existence is incompatible with ours. Their ships, their technology, even their bodies would instantly be destroyed upon contact with regular matter. This makes the idea of direct interaction between matter and antimatter civilizations almost impossible, but it also raises profound questions about the nature of the universe. If antimatter galaxies exist, do they have their own version of physics? Are there subtle differences in how antimatter interacts with the fundamental forces of nature? Some theories suggest that antimatter could respond differently to gravity, meaning an antimatter galaxy might behave in ways that don't completely match our expectations. If that were the case, it could help explain some of the biggest mysteries in cosmology, such as dark energy and the unexplained expansion of the universe. One of the biggest mysteries in modern physics is why the universe is expanding at an accelerating rate. Scientists attribute this to dark energy, an unknown force that makes up about 68% of the cosmos. But what if the answer isn't dark energy at all? What if the presence of antimatter galaxies, hidden far beyond our reach, is affecting the large-scale structure of the universe? Some physicists have proposed that antimatter might generate a form of negative gravity, meaning that instead of attracting normal matter, it repels it. If that were true, antimatter galaxies could be pushing the universe apart, contributing to the acceleration we observe today. This idea is still highly speculative, but if it were proven, it would completely change our understanding of how the universe works. It would mean that instead of being a strange leftover from the early universe, antimatter could be playing an active role in shaping the cosmos on the largest scales. It would also mean that the search for antimatter galaxies isn't just a quest to find something exotic. It could be the key to answering some of the biggest questions in physics. But what if we never find an antimatter galaxy? What if all the antimatter from the early universe was truly annihilated, leaving only matter behind? That would still be a major mystery because it would mean that something, at some point, created an imbalance between matter and antimatter. Whatever process allowed matter to win out must have been incredibly precise, happening on a scale so fundamental that it shaped the entire history of the cosmos. Scientists are still searching for this answer, and until we find it, the possibility of antimatter galaxies remains one of the greatest space mysteries of all time. If antimatter galaxies do exist, one of the biggest challenges in proving their existence is that they would be almost completely invisible to our current methods of observation. Normal galaxies are detected by the light they emit, the radiation they produce, and the gravitational effects they have on their surroundings. But an antimatter galaxy would emit light just like a regular one. Its stars would burn using nuclear fusion, producing the same types of radiation we're used to seeing from matter-based stars. This means that an antimatter galaxy, even if it were right in front of us, would look identical to any other galaxy we've discovered. The only surefire way to confirm an antimatter galaxy would be to detect interactions between its antimatter and our normal matter. If matter and antimatter were to meet at the boundary between a normal galaxy and an antimatter galaxy, they would annihilate each other in powerful gamma-ray bursts. These bursts would be unmistakable, far stronger than any natural astronomical event, and they would appear at the edges of these galaxies rather than deep within them. But despite scanning the universe for decades, astronomers have never found a pattern of gamma-ray emissions that would suggest entire galaxies made of antimatter. One of the main reasons scientists even consider the possibility of antimatter galaxies is that, theoretically, the Big Bang should have produced equal amounts of matter and antimatter. If that were the case, then at least some large regions of antimatter should have survived into the present day. However, the universe as we know it is overwhelmingly made of matter, and we still don't fully understand why. This is known as the baryon asymmetry problem, the question of why our universe is composed almost entirely of matter rather than a balance between matter and antimatter. One theory is that a slight imbalance in the early universe caused matter to outnumber antimatter. Some unknown process could have favored matter over antimatter, leading to the universe we see today. But another possibility is that antimatter wasn't entirely destroyed and instead formed its own isolated regions in the universe, far beyond our observable reach. If the latter is true, it means that antimatter galaxies could be lurking in the deep cosmos, separated from normal matter by vast cosmic voids. Cosmic voids are some of the most mysterious structures in the universe. They are enormous regions of space that contain very few galaxies, stretching for hundreds of millions of light-years. Some scientists have suggested that these voids could serve as natural boundaries between regions of normal matter and antimatter. If an antimatter galaxy existed beyond one of these voids, it might remain undetected because it would be too far away to interact with normal matter. This would explain why we haven't seen any telltale annihilation signatures. Another approach to detecting antimatter galaxies involves studying cosmic rays, high-energy particles that travel through space at nearly the speed of light. If an antimatter galaxy exists, some of its antimatter particles could be ejected into space and eventually make their way to Earth. The Alpha Magnetic Spectrometer on the International Space Station has been searching for these particles, particularly antihelium nuclei. If even a few of these particles were found, it would suggest that antimatter structures exist somewhere in the universe. So far, scientists have detected some candidate particles that could be antihelium, but the evidence isn't strong enough to confirm anything yet. If future experiments definitively detect antihelium, it would be one of the biggest discoveries in physics, proving that large-scale antimatter structures exist somewhere in the universe. But let's consider an even more mind-bending possibility. What if an antimatter galaxy is closer than we think? What if there is an entire antimatter star system hiding somewhere in our own galaxy? If a single star or even a small cluster of stars were made of antimatter, they would still appear completely normal to our telescopes. The only way we would detect them is if they interacted with surrounding matter in some way. For example, if an antimatter star were to pass through a dust cloud made of normal matter, the annihilation of particles would create a burst of gamma rays. Scientists have been searching for these unusual bursts, but so far, nothing has been found that definitively points to an antimatter star. However, space is vast, and our galaxy alone contains hundreds of billions of stars. It's possible that an antimatter star or even a small antimatter solar system exists in a region we haven't studied closely yet. If antimatter galaxies do exist, they could hold the key to answering fundamental questions about physics. For instance, one of the biggest unsolved mysteries is whether antimatter behaves the same way as normal matter in a gravitational field. We assume that antimatter is attracted by gravity just like normal matter, but this has never been directly tested on a large scale. If antimatter repels normal matter instead of attracting it, then an antimatter galaxy might behave differently than we expect, perhaps explaining some of the anomalies we see in cosmic expansion. Some theories suggest that if antimatter had different gravitational properties, it could contribute to the effects that we currently attribute to dark matter or dark energy. Dark matter is thought to make up about 27% of the universe, but we still don't know what it is. If antimatter interacts with gravity in an unexpected way, it might mean that some of what we call dark matter is actually antimatter in disguise, hidden away in distant galaxies that we can't distinguish from normal ones. This idea is controversial because no experiment has ever shown that antimatter behaves differently under gravity. But if an antimatter galaxy were found, it would give scientists a real-world case study to test these ideas. Observing how an antimatter galaxy moves, how its stars orbit, and how it interacts with the cosmic web could provide insights that completely reshape our understanding of the universe. Even if we never find an antimatter galaxy, the mere possibility of its existence challenges our assumptions about the cosmos. It forces us to question why the universe is the way it is, why matter won out over antimatter, and whether hidden regions of antimatter are still out there, beyond our ability to detect. Every time scientists develop a new tool or a more powerful telescope, the question of antimatter galaxies resurfaces. With each technological advancement, we get one step closer to either proving or ruling out their existence. If we do find an antimatter galaxy, it will be one of the most groundbreaking discoveries in history. It would mean that the universe is far more complex than we ever imagined. It would also raise profound questions about how antimatter and matter regions formed, whether there are natural barriers keeping them apart, and what role antimatter plays in the evolution of the cosmos. Until that day comes, the mystery remains unsolved. Are there entire galaxies made of antimatter hiding in the deepest reaches of space? Or is our universe truly dominated by matter alone? The answer could be waiting in the cosmic voids, in the unexplored depths of the universe, or in the data of a future experiment that has yet to be conducted. One thing is certain, the search for antimatter galaxies isn't over, and as long as the mystery persists, scientists will keep looking for answers. If antimatter galaxies do exist, they might be remnants of an early cosmic balance that was somehow broken. This would mean that the universe didn't just randomly end up with more matter than antimatter, but rather, some regions remained dominated by antimatter while others became purely matter-based. If that's the case, there could be vast stretches of the universe that are still almost entirely composed of antimatter, separated from us by distances so immense that we have yet to detect them. One of the most compelling reasons to consider the existence of antimatter galaxies is the possibility that the laws of physics could allow such structures to form naturally. If matter and antimatter were originally produced in equal amounts, but then separated, it's possible that the universe evolved in such a way that antimatter galaxies formed in isolated regions, far from our own. However, this raises another question: how did these antimatter galaxies avoid being annihilated by nearby matter? The only plausible explanation would be that they formed in regions where there was very little normal matter to begin with. This could mean that at some point in the early universe, matter and antimatter were somehow pushed apart, perhaps by an unknown force or a fundamental asymmetry in how the universe expanded. Some physicists speculate that this separation might be linked to the inflationary period of the universe, when space itself expanded at an incredible rate just moments after the Big Bang. If an antimatter galaxy exists on the other side of the observable universe, its interactions with surrounding matter would be minimal. It would exist in its own isolated pocket of space, far from anything that could cause large-scale annihilation. This could explain why we haven't detected any telltale gamma-ray bursts from the destruction of matter and antimatter. However, it doesn't rule out the possibility that smaller-scale annihilation events could still occur at the boundaries of these regions. One of the most exciting possibilities is that future space missions could help us detect signs of antimatter galaxies by sending probes beyond our immediate cosmic neighborhood. As we develop more advanced spacecraft and deep space observation technologies, we might eventually be able to detect antimatter cosmic rays or even send probes to the far reaches of our galaxy to analyze intergalactic particles. If we could find even a single antimatter particle in deep space that originated from an antimatter galaxy, it would be the ultimate proof that such structures exist. Another avenue for discovering antimatter galaxies lies in the study of the cosmic microwave background radiation, the faint glow left over from the Big Bang. This radiation carries information about the universe's earliest moments, and could hold clues about whether antimatter galaxies were ever part of the cosmic structure. Some scientists believe that subtle anomalies in the cosmic microwave background might indicate regions where antimatter was once abundant. If this turns out to be true, it could provide the first indirect evidence that antimatter galaxies exist beyond our observable universe. However, there is another possibility that could explain why we don't see antimatter galaxies. What if antimatter behaves differently than we expect? The standard model of physics assumes that antimatter obeys the same physical laws as normal matter, including gravity. But what if antimatter has slightly different properties that prevent it from forming large-scale structures like galaxies? Some theories suggest that antimatter might have a different gravitational interaction than regular matter, meaning that instead of clustering into galaxies, it could be spread out more evenly across the universe. If this were true, then antimatter galaxies might not exist at all because antimatter wouldn't behave in a way that allows it to form dense structures. This leads to an even deeper question: could antimatter have played a role in shaping the large-scale structure of the universe? If antimatter interacts with gravity in an unexpected way, it could help explain some of the mysteries surrounding dark energy and the accelerated expansion of the universe. Dark energy is thought to be the force that is causing the universe to expand at an increasing rate, but no one knows exactly what it is. Some researchers have speculated that antimatter could contribute to this effect, either by repelling normal matter or by creating subtle distortions in the fabric of spacetime. If an antimatter galaxy were discovered, it would revolutionize our understanding of physics. It would force scientists to rethink the entire history of the universe, from the Big Bang to the formation of cosmic structures. It would also raise new questions about whether antimatter galaxies could support life. If an antimatter planet existed, could it develop antimatter-based life forms? Would these life forms experience physics differently than we do? And what would happen if an antimatter civilization somehow made contact with a matter-based civilization? For now, the existence of antimatter galaxies remains one of the greatest mysteries in astrophysics. The search continues, and with each new experiment and technological advancement, we come closer to finding an answer. Whether these galaxies are hiding in the most distant corners of the cosmos, or whether they never formed at all, their potential existence challenges everything we think we know about the universe. The next breakthrough in physics could come from the discovery of an antimatter galaxy, a finding that would rewrite the fundamental rules of science. The idea of an antimatter galaxy existing somewhere in the universe isn't just a wild hypothesis, it's a direct consequence of the biggest unsolved mystery in physics. Why does our universe contain so much more matter than antimatter? The laws of physics, as we currently understand them, suggest that matter and antimatter should have been created in equal amounts during the Big Bang. If that were true, then the universe should have annihilated itself almost immediately, leaving nothing but energy behind. And yet, here we are, in a cosmos filled with matter, stars, planets, and galaxies, with no confirmed traces of large-scale antimatter structures. But what if the universe didn't get rid of all its antimatter? What if, somewhere in the vast expanse of space, entire galaxies exist that are composed of antimatter instead of regular matter? If that were the case, these antimatter galaxies would look almost identical to the ones we see today. Same structure, same formation processes, same laws of physics governing them. The only difference would be that everything inside them, from the stars to the planets to the potential life forms that might inhabit them, would be made entirely of antimatter. The reason this idea is so intriguing is that, theoretically, there's nothing stopping antimatter galaxies from existing. If an antimatter galaxy were located far enough away from a matter-dominated region of the universe, it could persist indefinitely without ever encountering enough matter to trigger large-scale annihilation. But that raises another question. If antimatter galaxies exist, why haven't we detected them yet? One of the biggest challenges in proving or disproving the existence of antimatter galaxies is that antimatter behaves exactly like normal matter, until it comes into contact with matter itself. If we were looking at an antimatter galaxy through a telescope, it would emit the same type of light as a normal galaxy. The same nuclear fusion processes that power stars in a matter-based galaxy would be at work in an antimatter galaxy, producing identical radiation signatures. This means that, purely from an observational standpoint, an antimatter galaxy would be virtually indistinguishable from a regular galaxy. The only surefire way to identify an antimatter galaxy would be to find evidence of antimatter-matter annihilation occurring at the boundaries between matter and antimatter regions of space. This annihilation process releases high-energy gamma rays, which should be detectable if a matter-dominated region of space were interacting with an antimatter-dominated region. However, despite decades of searching, astronomers have not observed any large-scale gamma-ray emissions that would indicate the presence of entire antimatter galaxies. But that doesn't mean they don't exist. One possibility is that any antimatter galaxies that do exist are so far away from us that they're beyond the observable horizon of the universe. Because of the universe's expansion, there's a limit to how far we can see, around 46 billion light-years in any direction. If an antimatter galaxy were located beyond this horizon, we simply wouldn't be able to detect it. Another possibility is that antimatter galaxies could exist in isolated pockets of the universe where they are effectively sealed off from matter-dominated regions. If these antimatter regions formed in the early universe and were separated from the rest of the cosmos by vast voids, they could exist undisturbed, never coming into contact with enough matter to produce noticeable gamma-ray emissions. Some researchers have proposed that we could look for antimatter signatures using cosmic rays, high-energy particles that travel through space. If antimatter galaxies exist, some of the cosmic rays that reach us should include antihelium nuclei, which are composed entirely of antimatter. Detecting even a few antihelium particles in cosmic rays would be a major breakthrough, as it would suggest the existence of large antimatter structures somewhere in the universe. So far, there have been a few tantalizing hints of antihelium particles detected by experiments, like the alpha magnetic spectrometer aboard the International Space Station, but nothing conclusive yet. The question of antimatter galaxies also leads to some truly mind-bending implications. If entire galaxies of antimatter exist, could there be antimatter life forms? Could an antimatter civilization have evolved somewhere in the cosmos, unaware that they are fundamentally different from the matter-based civilizations that may exist elsewhere? If an antimatter civilization ever tried to make contact with a matter-based one, the consequences would be catastrophic. because the moment matter and antimatter meet, they annihilate each other in a burst of energy. But what if an advanced civilization had already figured out a way to manipulate antimatter without causing annihilation? If we could harness antimatter safely, it could be the ultimate energy source. If an antimatter-based civilization had found a way to generate and control antimatter efficiently, they might possess a nearly limitless energy supply. This brings up an even more profound question. Could an advanced alien civilization be hiding within an antimatter galaxy, completely undetectable to us because we are only looking for matter-based life? Our entire approach to searching for extraterrestrial civilizations assumes that they are made of the same kind of matter we are. But if a highly advanced civilization had evolved in an antimatter galaxy, their technology, and even their fundamental perception of the universe might be so different from ours that we wouldn't even know where to begin looking. There is also the possibility that antimatter galaxies played a crucial role in the early history of the universe. Some physicists believe that the presence of antimatter regions could help explain some of the biggest mysteries in cosmology, including the apparent imbalance between matter and antimatter. If the early universe contained both matter and antimatter galaxies that later became separated, this could provide clues about why our local universe is so overwhelmingly matter-dominated today. Some alternative theories suggest that antimatter might interact with gravity differently than regular matter. According to these ideas, antimatter could have a kind of negative gravity effect, meaning it would repel normal matter rather than attract it. If this were the case, antimatter galaxies might be responsible for some of the strange phenomena we currently attribute to dark energy, the mysterious force that seems to be accelerating the expansion of the universe. The hunt for antimatter galaxies is far from over. Scientists are constantly developing new ways to test for the presence of antimatter in space, from searching for unique cosmic ray signatures to scanning deep space for unexplained gamma-ray bursts. The next breakthrough in our understanding of antimatter could come from an unexpected discovery, a signal hidden in the vast cosmic background radiation, an anomaly in the data collected from space probes, or even an entirely new physics experiment that changes the way we think about the universe. If we do eventually discover an antimatter galaxy, it would be one of the most revolutionary discoveries in human history. It would force us to rethink the nature of the universe, the fundamental forces that govern reality, and even the possibility that life might exist in forms that we have never even imagined. It would be a moment that redefines our place in the cosmos, proving that the universe is far stranger and more complex than we ever believed. The mystery of antimatter galaxies remains one of the most compelling unsolved questions in astrophysics. Whether they exist or not, their potential existence challenges everything we know about the universe. And as technology advances, as we push the boundaries of space exploration and scientific discovery, we may one day find the answer. Until then, the possibility remains, out there, somewhere in the vast and uncharted reaches of the cosmos, an entire galaxy made of antimatter could be silently orbiting, waiting for us to uncover its secrets. One of the most puzzling questions about antimatter galaxies is their potential role in the grand structure of the cosmos. If such galaxies exist, are they scattered randomly throughout the universe, or do they form their own distinct antimatter regions? Some theories suggest that if antimatter galaxies are real, they might not be evenly distributed among normal galaxies but instead exist in their own large-scale structures, separated from matter-dominated regions by immense cosmic voids. The reason behind this speculation lies in the fundamental nature of how galaxies form. Matter tends to clump together due to gravitational attraction, forming galaxies, clusters, and superclusters over billions of years. If antimatter galaxies formed alongside matter galaxies, but remained isolated from them, this could imply that large portions of the universe are antimatter-dominated without us realizing it. These antimatter regions could be completely undetectable unless they somehow interact with matter-based structures at their boundaries. Some scientists have proposed that the cosmic web, the vast structure of filaments and voids that make up the large-scale distribution of matter in the universe, might actually contain separate regions for antimatter galaxies. If this were the case, then our observable universe might only represent a part of a much more complex reality, where entire clusters of galaxies are made of antimatter but are hidden from our detection due to the lack of direct interaction with matter. If antimatter galaxies exist, Another major question arises: how did they form? Current cosmological models assume that the universe should have been born with an equal amount of matter and antimatter, yet for some unknown reason, the balance was tipped in favor of matter. However, what if instead of a complete dominance of matter, the early universe actually split into distinct regions, some dominated by matter, others by antimatter? One theory suggests that during the first moments of the Big Bang, fluctuations in energy density could have led to the creation of separate zones, where some regions ended up being matter-dominated while others became antimatter-dominated. If these regions remained separate as the universe expanded, then antimatter galaxies could exist in isolated bubbles of space, far away from the matter-dominated regions we observe. But if this is the case, why haven't we detected any evidence of these regions colliding with each other? One possible answer is that these antimatter galaxies, if they exist, are so far away that they have not yet had time to interact with our matter-dominated part of the universe. The universe is constantly expanding, and if antimatter galaxies formed in regions that were already receding from us at near light speeds, they could remain beyond our observational reach indefinitely. There's also the question of dark matter. Dark matter is one of the biggest mysteries in modern physics, an invisible substance that makes up most of the mass in the universe, yet does not interact with light or ordinary matter in any detectable way. Some researchers have speculated that antimatter galaxies might actually be connected to the mystery of dark matter. If antimatter behaves differently under gravity, perhaps repelling normal matter instead of attracting it, then it could provide an alternative explanation for the strange gravitational effects we currently attribute to dark matter. If antimatter galaxies interact with gravity in an unexpected way, it could mean that our current understanding of how gravity works on cosmic scales is incomplete. This would have profound implications for physics, requiring new theories that go beyond Einstein's general relativity. Some scientists have even proposed that antimatter might be linked to dark energy, the force responsible for the accelerating expansion of the universe. If antimatter has a repulsive gravitational effect, it could help explain why galaxies are moving away from each other at increasing speeds. But let's take this idea even further. If antimatter galaxies exist, could they host antimatter-based life forms? This is one of the most fascinating and speculative ideas in astrophysics. Theoretically, there is nothing preventing life from developing in an antimatter-dominated environment. Just as regular matter can form complex molecules, antimatter should be able to do the same. In an antimatter galaxy, stars would burn just like normal stars, planets would form just like normal planets, and under the right conditions, life could emerge. If an antimatter civilization exists, it might not even realize that it is different from us. To them, their version of chemistry and biology would seem completely normal. The real danger would arise if an antimatter civilization ever tried to interact with a matter-based civilization like ours. The moment antimatter comes into contact with matter, it annihilates in a burst of pure energy. This means that an antimatter spaceship entering a matter-dominated region of space would be instantly destroyed upon contact with even the smallest amount of matter. This raises another interesting question. If an antimatter civilization has advanced technology, could they have figured out a way to safely contain antimatter and prevent it from annihilating when it comes into contact with normal matter? If so, this could lead to an entirely new realm of possibilities for space exploration and energy generation. One of the most exciting experiments related to antimatter today is the search for antihelium in cosmic rays. If antihelium is detected in space, it would be one of the strongest pieces of evidence that large-scale antimatter structures exist. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, and they occasionally contain exotic particles that provide clues about the composition of the universe. If we find antihelium nuclei in cosmic rays, it could indicate that some antimatter galaxies or antimatter regions exist. The Alpha Magnetic Spectrometer, AMS-02, a particle physics experiment mounted on the International Space Station, is one of the leading efforts to detect antimatter in cosmic rays. So far, there have been a few potential detections of antihelium, but no definitive confirmation yet. If AMS-02 or future experiments find conclusive evidence of antimatter in space, it could revolutionize our understanding of the universe. But let's consider the philosophical implications of antimatter galaxies. If entire regions of the universe are made of antimatter, it could mean that our understanding of reality is far more complex than we ever imagined. Could there be an antimatter version of our own Milky Way? An antimatter Earth? An antimatter version of you, living in an antimatter galaxy, completely unaware that they are composed of something fundamentally different from the matter we know. This leads into the concept of parallel universes and mirror worlds. Some theories suggest that our universe might not be the only one, that there could be an infinite number of parallel universes, each with different properties. If antimatter galaxies exist, could they be connected to an even deeper level of reality, one where matter and antimatter are balanced across multiple universes? The search for antimatter galaxies is one of the most compelling frontiers in astrophysics. While we have yet to find definitive proof that they exist, the possibility remains open, and every new experiment brings us closer to solving this cosmic mystery. Whether or not we ever find an antimatter galaxy, the mere fact that the question exists pushes the boundaries of human knowledge and challenges us to rethink everything we know about the universe. The universe is vast, mysterious, and full of surprises. If antimatter galaxies are out there, they could hold the key to some of the deepest secrets of physics, from the nature of dark matter to the origins of the cosmos itself. And one day, perhaps, we will finally discover the undeniable proof that somewhere, hidden in the depths of space, an entire galaxy made of antimatter is waiting to be found. One of the most fascinating aspects of the antimatter galaxy hypothesis is the possibility that our universe has a hidden symmetry, one where antimatter galaxies exist in a way that perfectly balances the matter we observe. In physics, symmetry plays a crucial role in shaping our understanding of natural laws. The idea that every fundamental particle has an antimatter counterpart suggests that nature might favor a kind of balance, even on the grandest cosmic scales. But if that were true, then why don't we see signs of this balance in everyday life? Why is the observable universe overwhelmingly composed of matter, with only trace amounts of antimatter appearing naturally? This question has led scientists to propose the idea that the universe might be structured in a way that keeps matter and antimatter galaxies separate, either through vast cosmic voids or through fundamental properties of spacetime that prevent large-scale mixing. One of the key theories attempting to explain this separation is related to baryon asymmetry. The early universe should have created equal amounts of matter and antimatter, but for some reason, matter came to dominate. However, what if the imbalance only applies to the part of the universe we can see? What if there are entire regions beyond our observational horizon that contain antimatter galaxies, completely hidden from our view? This idea aligns with the inflationary model of the early universe. According to inflation theory, the universe underwent an exponential expansion in the first fractions of a second after the Big Bang. If different regions of the universe had slightly different initial conditions, some areas could have ended up being matter-dominated, while others became antimatter-dominated. These regions might be so far apart that they have never had a chance to interact, leaving us with a universe where matter dominates our local observable patch, but antimatter dominates in others. If this is the case, then how could we ever detect an antimatter galaxy? One possibility is that, at the boundaries where matter and antimatter regions meet, we would expect to see high-energy gamma-ray emissions. When matter and antimatter collide, they annihilate, producing a characteristic signature of gamma rays. Yet, despite extensive searches using powerful space telescopes like Fermi Gamma-Ray Space Telescope, no such large-scale annihilation signals have been detected. This could mean one of two things: either antimatter galaxies do not exist, or they are so isolated that they rarely interact with matter. If antimatter galaxies are out there but are completely separated from matter regions, then they could remain effectively invisible, existing in their own cosmic bubble without ever making contact with the part of the universe we inhabit. However, some researchers have suggested that there might be subtler ways to detect antimatter galaxies. One approach is to look for cosmic rays that contain antimatter particles that could have originated from an antimatter galaxy. As mentioned earlier, experiments like the Alpha Magnetic Spectrometer, AMS-02, on the International Space Station have been searching for antihelium nuclei, which would be a strong indicator that large-scale antimatter structures exist. Another approach involves studying the cosmic microwave background (CMB), the afterglow of the Big Bang. If the universe contains antimatter galaxies, they might leave subtle imprints on the CMB due to differences in how matter and antimatter interact with radiation over cosmic time. Advanced space telescopes analyzing the CMB could potentially reveal these differences, providing indirect evidence for the existence of antimatter regions. But let's take this idea even further. If an antimatter galaxy exists, what would it actually look like? In many ways, it would appear almost identical to a normal galaxy. It would have stars, planets, nebulae, and black holes, just like a regular galaxy. However, everything in that galaxy would be composed of antimatter, antiprotons instead of protons, positrons instead of electrons, and antineutrons instead of neutrons. From a purely visual perspective, there would be no obvious way to distinguish an antimatter galaxy from a regular galaxy unless we had the means to interact with it. If we could somehow send a probe into an antimatter galaxy, the moment it made contact with any antimatter particles, it would instantly be annihilated. This means that any attempt to explore an antimatter galaxy using normal matter spacecraft would be impossible without some form of advanced containment technology. But what if an antimatter civilization exists within an antimatter galaxy? Would they be aware that they are made of antimatter? To them, everything would appear normal. Their chemistry, physics, and even potential biological processes would function just like ours. However, if they developed advanced science, they might eventually realize that their fundamental particles have opposite charge properties compared to those in a matter-based universe. If an antimatter civilization reached a level of technological advancement where they could explore beyond their galaxy, they might eventually discover our matter-dominated universe and face the same challenges we would in exploring their antimatter world. If they ever attempted to make contact with a matter-based civilization, they would face the existential problem that direct physical interaction would be impossible due to the immediate annihilation of matter and antimatter. This brings us to an even more intriguing possibility. Could an antimatter civilization develop the technology to safely interact with matter-based civilizations? If they discovered a way to create a protective barrier that prevents annihilation, it would open the door to an entirely new form of intergalactic communication. This would require a level of scientific advancement far beyond anything we currently understand, potentially involving exotic physics, quantum field manipulation, or even higher dimensional technology that allows for matter-antimatter interaction without destruction. If such technology were possible, it might already be in use. Could UFO sightings or unexplained space phenomena be evidence of antimatter civilizations attempting to interact with our matter-based universe? While this is purely speculative, it raises fascinating questions about the nature of intelligent life and the possibilities of communication across different fundamental structures of reality. Another major question regarding antimatter galaxies is whether they could serve as a source of energy. Since matter and antimatter annihilate upon contact, they release massive amounts of energy, far more than any chemical or nuclear reaction. If we could find a way to safely harvest antimatter from space, it could revolutionize energy production, providing an almost limitless power source. Some scientists have proposed that if antimatter galaxies exist, we could one day develop technology to extract small amounts of antimatter and use it for advanced propulsion systems, space travel, or even energy production on Earth. However, this would require overcoming enormous technological hurdles, including containment systems that prevent premature annihilation. In the grand scheme of the universe, the existence of antimatter galaxies could be one of the most profound discoveries ever made. If they exist, they would challenge our fundamental understanding of physics, force us to rethink the origins of the cosmos, and potentially provide insights into some of the biggest mysteries in science, including dark matter, dark energy, and the true nature of space-time. The search for antimatter galaxies continues, and while no definitive evidence has been found yet, every new discovery in astrophysics brings us one step closer to answering this cosmic mystery. Whether they exist in distant, unreachable regions of the universe, hidden beyond our observational limits, or whether they remain a theoretical possibility that nature never realized, the question itself pushes the boundaries of human curiosity. Perhaps one day, with more advanced technology, we will finally uncover the truth about antimatter galaxies. Until then, the mystery remains, waiting for us to solve it. The idea of an antimatter galaxy is not just a theoretical curiosity. It's a doorway into some of the biggest unsolved questions in physics. If even a single antimatter galaxy exists somewhere in the universe, it would mean that our understanding of the fundamental laws of nature is incomplete. It would challenge the standard cosmological model and force us to reconsider why the observable universe is almost entirely made of matter. One of the most perplexing aspects of this mystery is the question of why matter and antimatter did not completely annihilate each other in the early universe. If equal amounts of matter and antimatter were created in the Big Bang, they should have annihilated into pure energy, leaving behind nothing but light. Yet here we are, living in a universe filled with galaxies, stars, planets, and life, all composed of matter. This imbalance, known as baryon asymmetry, is one of the biggest open questions in physics. Some theories suggest that in the very early universe, tiny asymmetries in physical laws favored the survival of matter over antimatter. Processes involving fundamental particles and forces, particularly in the realm of quantum physics, may have created a slight excess of matter over antimatter. Even if the difference was as small as one extra matter particle for every billion matter-antimatter pairs, that tiny imbalance would have been enough to form the matter-dominated universe we see today. But what if that imbalance was not universal? What if instead of a slight excess of matter everywhere, the universe was divided into regions, some where matter dominated and others where antimatter took over? If that were the case, then antimatter galaxies could exist in vast, isolated pockets of the cosmos, separated from our matter-dominated region by immense cosmic voids. This idea leads to another fascinating possibility. What if our observable universe is just one part of a much larger, structured system where matter and antimatter galaxies exist in a kind of cosmic checkerboard pattern? In such a scenario, massive cosmic voids, regions of space almost completely empty of galaxies, might act as natural barriers, preventing large-scale interactions between matter and antimatter regions. But even if antimatter galaxies exist in isolated regions, wouldn't we see some evidence of them? One potential clue lies in the mysterious nature of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, and some of them have been found to contain positrons, the antimatter counterpart to electrons. While most positrons can be explained by conventional astrophysical processes, some appear to be coming from unknown sources. Could these be traces of antimatter galaxies beyond our observable reach? The Alpha Magnetic Spectrometer, AMS-02, a particle physics experiment mounted on the International Space Station, has been searching for antimatter cosmic rays for years. In 2017, AMS-02 detected several antihelium nuclei, particles that should not exist in large quantities if our universe is entirely matter-dominated. The presence of antihelium suggests the possibility that somewhere, antimatter is forming into complex structures like stars or even entire galaxies. However, detecting antimatter galaxies is incredibly difficult. If an antimatter galaxy is located far beyond our observable universe, its light would reach us just like the light from a regular matter galaxy. The reason is that photons, the particles that make up light, are neither matter nor antimatter, they are neutral. This means that if an antimatter star emits light, it would look identical to the light from a regular matter star. Without direct interaction, an antimatter galaxy would be essentially invisible to us, blending into the background of normal galaxies. But what if there was a way to detect antimatter galaxies indirectly? One approach involves looking for signs of high-energy gamma-ray emissions at the boundaries of matter and antimatter regions. When matter and antimatter come into contact, they annihilate and produce gamma rays with a very specific energy signature. If we could detect unusual gamma-ray patterns in certain parts of the universe, it could be a sign that an antimatter region is interacting with a matter region. Yet, so far, no large-scale gamma-ray signals have been found that indicate the presence of antimatter galaxies. This suggests one of two things: either antimatter galaxies do not exist, or they are so completely isolated that they never interact with matter galaxies in any meaningful way. If antimatter galaxies do exist but are hidden beyond our observational limits, we may need entirely new methods of detection to prove their existence. One potential avenue for future research is gravitational waves. Gravitational waves are ripples in space-time caused by massive objects moving through the universe, and they can be detected even from extremely distant sources. If antimatter galaxies exist, they should behave gravitationally just like matter galaxies, producing detectable gravitational wave signatures. If scientists can find any unusual patterns in gravitational wave data that cannot be explained by known matter-based galaxies, it could provide indirect evidence of antimatter galaxies. Another possibility is that antimatter galaxies could be connected to the mystery of dark matter. Dark matter is an invisible substance that makes up about 85% of the matter in the universe, but its true nature remains unknown. Some theories suggest that dark matter could be made of exotic particles that interact weakly with normal matter, and one speculative idea is that antimatter galaxies could play a role in this hidden structure of the cosmos. If antimatter galaxies emit some form of weakly interacting particles that behave like dark matter, then their existence could help explain the missing mass in the universe. But perhaps the most intriguing question is whether an antimatter galaxy could support life. If an antimatter galaxy exists somewhere in the universe, then in theory, it could contain antimatter planets, antimatter atmospheres, and even antimatter life forms. Such life forms would not be aware that they were made of antimatter. To them, their world would feel just as normal as ours does to us. But if an antimatter civilization ever developed the ability to explore beyond their galaxy, they might eventually discover that other parts of the universe are made of matter, and that contact with matter would be catastrophic. Could an antimatter civilization have already discovered us? If an antimatter species is technologically advanced enough to detect matter-based galaxies, they might be studying us from afar, unable to make direct contact without risking annihilation. If they have developed advanced physics beyond our understanding, they may have even found a way to shield themselves from the destructive effects of matter-antimatter interactions, allowing for potential communication across the cosmic divide. This leads to an even bigger question. If an antimatter galaxy exists, what does that say about the nature of the universe itself? Could the universe be more balanced than we currently realize, with matter and antimatter coexisting on cosmic scales in a way we have yet to detect? Or is it possible that our understanding of physics is incomplete, and there are unknown forces at play that determine why matter dominates in our observable region? The search for antimatter galaxies continues, and while no definitive proof has been found yet, every new discovery in astrophysics brings us closer to answering this profound question. Whether they exist in hidden corners of the universe, beyond our reach, or remain only a theoretical possibility, the mystery of antimatter galaxies pushes the boundaries of human curiosity. Perhaps one day, with more advanced telescopes, particle detectors, and a deeper understanding of physics, we will finally uncover the truth about antimatter galaxies. Until then, the question remains open, waiting for the right discovery to change everything we thought we knew about the cosmos. The search for antimatter galaxies is not just a scientific curiosity, it's a quest to understand one of the most fundamental mysteries of the universe. If an antimatter galaxy exists, it would mean that nature has found a way to segregate matter and antimatter on a cosmic scale, keeping them apart long enough to form stars, planets, and possibly even life. But if no antimatter galaxies exist, it would reinforce the idea that some unknown process in the early universe tipped the balance in favor of matter, leading to the universe we see today. One of the most frustrating aspects of this mystery is that our current methods of detection may not be sufficient to find an antimatter galaxy, even if one exists. Traditional telescopes rely on detecting light, and since light itself is not matter or antimatter, an antimatter galaxy would appear indistinguishable from a normal galaxy. This means that if an antimatter galaxy is out there, it could be hiding in plain sight among the billions of galaxies we have already observed. Scientists have attempted to find indirect evidence of antimatter galaxies by looking for the telltale signs of matter-antimatter annihilation. If an antimatter galaxy were to come into contact with a matter galaxy, the resulting annihilation would produce an enormous amount of high-energy gamma rays. However, no large-scale gamma ray signals of this type have been detected, suggesting that if antimatter galaxies do exist, they are completely isolated from the matter-dominated regions of the universe. This brings us to another fascinating question. how would an antimatter galaxy form in the first place? The standard model of cosmology suggests that matter and antimatter were created in equal amounts during the Big Bang, but something caused matter to dominate. If an antimatter galaxy exists, then the process that led to this asymmetry must have been localized rather than universal. In other words, some regions of the universe may have remained antimatter-dominated while others became matter-dominated. One possible explanation involves the concept of cosmic inflation. During the earliest moments of the universe, a rapid expansion known as inflation stretched the fabric of space at an incredible rate. If inflation occurred in an uneven way, it could have separated regions of matter from regions of antimatter before they had a chance to annihilate each other. This could mean that entire antimatter galaxies exist in distant, isolated regions of the universe, beyond our ability to observe them. Another possible explanation is that certain fundamental forces of nature behave differently for matter and antimatter. Some experiments in particle physics have shown that certain reactions favor the production of matter over antimatter by a tiny fraction. If this bias existed in the early universe, it could have led to an uneven distribution of matter and antimatter, allowing some regions to form antimatter galaxies while others formed matter galaxies. Despite all these possibilities, the lack of direct evidence for antimatter galaxies remains a major challenge. The most compelling clue so far comes from the detection of antihelium nuclei in cosmic rays. These particles should not exist in large quantities if our universe is entirely matter-dominated. If future experiments confirm that antihelium is coming from deep space rather than from rare particle interactions near Earth, it could be a strong indication that antimatter galaxies are real. The next step in the search for antimatter galaxies will likely involve more sensitive particle detectors, better gamma-ray observatories, and possibly even gravitational wave studies. If antimatter galaxies exist, their interactions with normal matter, even at an extreme distance, might produce subtle gravitational effects that could be detected with future technology. But what if we never find an antimatter galaxy? Would that mean they don't exist, or could it mean that they are simply too far away or too well hidden for us to detect? The absence of evidence is not always evidence of absence. Until we have a complete understanding of why our universe contains so much more matter than antimatter, the possibility of antimatter galaxies remains one of the most intriguing mysteries in modern science. If an antimatter galaxy is ever discovered, it would not just be a scientific breakthrough. It would change our understanding of the universe on a fundamental level. It would mean that the cosmos is far stranger than we ever imagined, with vast regions where everything is made of antimatter, mirroring the matter-dominated universe we know. It would raise new questions about how these regions formed, how they remained separate, and whether they could ever come into contact. The search for antimatter galaxies is a testament to the human desire to understand the unknown. Even if we never find one, the effort to look for them pushes the boundaries of our knowledge and brings us closer to answering some of the most profound questions about the nature of reality. The universe is vast, mysterious, and full of surprises, and the possibility of an antimatter galaxy lurking somewhere in the cosmos is a reminder that there is still so much we have yet to discover. The idea that an antimatter galaxy could exist somewhere in the universe is both fascinating and unsettling. If such a galaxy exists, it raises profound questions about the very nature of the cosmos. Could there be entire regions of space where antimatter dominates, completely isolated from the matter-dominated universe we observe? And if so, why haven't we found them yet? One of the main reasons scientists suspect the existence of antimatter galaxies is the unresolved mystery of the matter-antimatter imbalance. The Big Bang should have produced equal amounts of matter and antimatter. But if that were the case, every particle of matter should have found an antimatter counterpart and annihilated, leaving behind nothing but energy. Clearly, that didn't happen, because our universe is filled with matter, stars, planets, galaxies, and even us. This leads to two possibilities. Either some unknown process tipped the balance in favor of matter, or antimatter exists in large, isolated pockets that we simply haven't detected yet. If the second possibility is true, then somewhere beyond our telescopes, antimatter galaxies could be drifting in the cosmic void, following the same physical laws as our own matter-based galaxies, but completely separate from them. But how would we find such a galaxy? The biggest challenge is that an antimatter galaxy would look almost exactly like a normal galaxy. A star made of antimatter would shine just as brightly as a star made of matter. The photons emitted by antimatter stars wouldn't behave any differently from normal light, making it almost impossible to distinguish an antimatter galaxy from a matter galaxy using traditional telescopes. This means that if antimatter galaxies exist, they could be hidden in plain sight. Some of the galaxies we've already observed could, in theory, be made of antimatter, and we wouldn't even know it. The only way to confirm their existence would be to detect the high-energy gamma rays produced when antimatter comes into contact with matter. If an antimatter galaxy were to interact with a matter galaxy, the border between them would be a violent region of annihilation, emitting an enormous amount of gamma radiation. But we haven't observed such signals on a cosmic scale, suggesting that if antimatter galaxies do exist, they must be extremely isolated. They would have to be located in vast voids of space, far from matter-dominated regions, where they never come into contact with normal matter. Another way scientists have searched for antimatter galaxies is by studying cosmic rays. If antimatter galaxies exist, they should occasionally send antimatter particles our way. In recent years, experiments like the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station have detected hints of antihelium nuclei, particles that should be incredibly rare in a matter-dominated universe. The discovery of antihelium in cosmic rays is intriguing because it suggests that something out there is producing antimatter in larger quantities than expected. If these particles are coming from deep space rather than local sources, they could be evidence of antimatter galaxies. However, more data is needed before scientists can confirm this possibility. If an antimatter galaxy does exist, what would it be like? In many ways, it would be almost identical to our own galaxy. It would have stars, planets, and possibly even life, all made entirely of antimatter. The fundamental forces that govern the universe would operate the same way, and from the perspective of an antimatter observer, everything would seem completely normal. But if an antimatter astronaut were to visit our galaxy, or if a matter-based astronaut were to visit an antimatter galaxy, the results would be catastrophic. The instant their spacecraft made contact with the other form of matter, it would annihilate in a flash of energy. Even a tiny speck of dust would be enough to trigger an explosion. This makes direct exploration of antimatter galaxies an almost impossible challenge. Despite these obstacles, the search for antimatter galaxies continues. Future space missions equipped with more advanced particle detectors could help solve the mystery. If scientists can confirm that antihelium is coming from deep space, it would be the strongest evidence yet that entire galaxies of antimatter exist somewhere in the universe. If we never find an antimatter galaxy, it would suggest that the early universe underwent some process that permanently tipped the balance in favor of matter. But if we do find one, it would be one of the most groundbreaking discoveries in the history of physics. It would force us to rethink everything we know about the structure of the cosmos, and could even open the door to new theories of physics that go beyond our current understanding. The possibility of antimatter galaxies reminds us that the universe is still full of mysteries. Even with all our technology, there are vast regions of space that remain unexplored. The existence of an antimatter galaxy, whether real or not, challenges us to keep pushing the boundaries of science, searching for answers to questions that could change our understanding of reality itself. The possibility of an antimatter galaxy existing somewhere in the universe forces us to rethink the way we understand cosmic evolution. If such a galaxy exists, it would mean that nature has somehow separated matter and antimatter on a grand scale, preventing their mutual annihilation while allowing both to form stars, planets, and perhaps even life. But if no antimatter galaxies exist, then the mystery of why our universe is made of matter deepens even further. Either way, the implications are staggering. One of the most frustrating aspects of this mystery is that even if an antimatter galaxy were right in front of us, we wouldn't necessarily know it. Unlike ordinary matter-antimatter collisions, which produce detectable gamma rays, an antimatter galaxy isolated from matter would emit light just like a normal galaxy. Its stars would burn just as brightly, and from a distance, it would be indistinguishable from the billions of galaxies we already see in the night sky. This means that if antimatter galaxies do exist, they must be completely isolated from matter galaxies, floating in vast cosmic voids where they never interact with ordinary matter. If an antimatter galaxy had ever come into contact with a normal galaxy, the annihilation at their boundary would have produced an intense burst of gamma radiation visible across the universe. Yet no such signals have been detected, suggesting that if antimatter galaxies are out there, they must be extremely rare or far away. But why would the universe have separated matter and antimatter in this way? One possible explanation involves the inflationary period of the early universe. Inflation theory suggests that in the first fraction of a second after the Big Bang, the universe underwent a rapid expansion, stretching space itself at an incredible rate. If, during this process, certain regions ended up dominated by matter while others were dominated by antimatter, it's possible that entire antimatter galaxies formed in regions completely disconnected from ours. Another potential explanation involves CP violation, a phenomenon in particle physics where the laws of nature seem to slightly favor matter over antimatter in certain interactions. While this asymmetry is tiny, if it existed in the early universe, it could have led to a gradual dominance of matter over antimatter. However, current measurements of CP violation aren't strong enough to fully explain why matter won out, leaving open the possibility that antimatter galaxies formed in isolated pockets of the universe. To test these theories, scientists have turned to cosmic ray studies. The Alpha Magnetic Spectrometer, AMS-02, mounted on the International Space Station, has detected hints of antihelium nuclei, particles that shouldn't exist in a matter-dominated universe. If future studies confirm that these particles are coming from deep space rather than local interactions, it could be the first concrete evidence that antimatter galaxies are real. If antimatter galaxies do exist, what would they be like? In almost every way, they would be mirror images of normal galaxies. They would contain antimatter stars, antimatter planets, and possibly even antimatter life. If an antimatter civilization existed, its inhabitants would see their world as completely normal, just as we see ours. The only difference would come if matter and antimatter ever met, because the result would be total annihilation. This raises another fascinating question: could an antimatter galaxy have intelligent life? If the laws of physics are the same, then there's no reason why life couldn't evolve in an antimatter galaxy just as it did in our own. The chemistry of antimatter atoms would be identical to that of normal atoms, meaning antimatter DNA, antimatter cells, and even antimatter ecosystems could exist. However, any contact between an antimatter civilization and our own would be catastrophic, as even the smallest interaction would lead to instant annihilation. The search for antimatter galaxies is ongoing, and future space missions may provide more answers. If we find evidence of large amounts of antimatter in deep space, it would confirm that the universe is far stranger than we ever imagined. If we don't, then we'll be left with an even deeper mystery. Why did our universe evolve to be dominated by matter, when it should have been equal parts matter and antimatter? The implications of this question go beyond just physics. They touch on the fundamental nature of reality itself. If an antimatter galaxy is found, it would mean that our universe is not as uniform as we once thought. It would mean that different regions of space follow different rules, shaped by unknown forces that have yet to be discovered. Even if we never find an antimatter galaxy, the search itself pushes the boundaries of what we know. The fact that we can even ask these questions, and build the technology to try to answer them, shows how far we've come in our understanding of the cosmos. But the biggest mysteries still remain. Is there an antimatter galaxy out there? If so, where? And if not, why did the universe choose matter over antimatter? Until we find definitive answers, the search continues. And as long as there are questions left to ask, the mystery of antimatter galaxies will remain one of the most intriguing puzzles in the universe. If an antimatter galaxy exists somewhere in the vast expanse of the universe, the consequences would be profound. It would confirm that nature has a way of separating matter and antimatter on a grand scale, possibly providing clues about why our observable universe is overwhelmingly composed of matter. But it would also raise a new set of questions that could challenge some of the fundamental principles of cosmology. One of the most perplexing aspects of this mystery is that, theoretically, the Big Bang should have produced equal amounts of matter and antimatter. If that had happened without any asymmetry, everything would have annihilated, leaving behind a universe filled with nothing but radiation. But since we exist, and we see galaxies, stars, and planets made of matter, it means something tipped the balance in favor of matter. However, if entire antimatter galaxies exist somewhere in the cosmos, it could mean that the universe found a way to separate the two instead of simply favoring one over the other. This idea brings up the possibility that space itself may have been structured in a way that created isolated regions dominated by either matter or antimatter. If this happened early in cosmic history, it would mean that antimatter galaxies formed just like our own but in regions where they would never interact with matter. This would explain why we haven't seen any large-scale annihilation events that would produce high-energy gamma-ray bursts. But there's another intriguing possibility. What if antimatter galaxies aren't entirely separate from matter galaxies, but instead exist in a cosmic balance that we haven't fully understood yet? What if the universe is like a checkerboard of matter and antimatter galaxies, carefully arranged in a way that prevents large-scale annihilation? Some theorists have suggested that if large-scale magnetic fields or unknown cosmic forces acted in a certain way, they might create barriers that keep matter and antimatter regions apart, preventing them from colliding. This would mean that antimatter galaxies might not be completely isolated in deep space but could be hiding in plain sight. In fact, some of the galaxies we've already observed might be made of antimatter, and we would have no way of knowing unless we could directly detect an interaction with matter. The only way to identify them would be to find evidence of antimatter particles escaping from their region of space and reaching our detectors. This is why cosmic ray experiments like the Alpha Magnetic Spectrometer, AMS-02, have become so important. The detection of antihelium nuclei in cosmic rays would be a major breakthrough, because these particles are nearly impossible to produce in significant quantities through known astrophysical processes. If antihelium is coming from deep space, it could be the first direct evidence that an entire region of the universe is made of antimatter. If this discovery is confirmed, it would lead to one of the biggest scientific revolutions in modern history. It would mean that our universe is not just a matter-dominated cosmos but a complex, dual-reality universe where antimatter exists on a galactic scale. This could change our understanding of fundamental physics, possibly leading to new theories about the origins of the universe, the nature of space-time, and even the possibility of new forms of energy extraction. One of the most mind-bending ideas is that if antimatter galaxies exist, they could have developed antimatter civilizations. This isn't just science fiction. The laws of physics suggest that antimatter life would behave just like ordinary life, with antimatter atoms forming antimatter molecules, antimatter cells, and even antimatter ecosystems. An antimatter planet orbiting an antimatter star would be just as habitable for antimatter beings as Earth is for us. But what would happen if a matter-based civilization and an antimatter civilization ever made contact? The result would be catastrophic. Any physical interaction between the two would lead to immediate annihilation, releasing enormous amounts of energy. Even a single atom of matter touching an atom of antimatter would trigger an explosion very powerful. This means that if an antimatter civilization ever attempted space travel and entered a matter-dominated region of the universe, their spacecraft wouldn't last a second. This raises an eerie question. Could it be that some antimatter civilizations have tried to explore space, only to meet instant annihilation upon encountering matter? If so, we would never know, because the explosion would leave no trace of their existence. The same danger applies to us. If we ever sent a probe into an antimatter region of space, it would be destroyed the moment it touched anything made of antimatter. Because of this, detecting an antimatter galaxy would have to be done from a safe distance. Scientists would need to rely on indirect methods, such as analyzing cosmic rays, searching for unusual gamma-ray emissions, or looking for signs of antimatter interactions in deep space. Future telescopes and space missions might be able to provide better data, but for now, the mystery remains unsolved. The idea of an antimatter galaxy is more than just a theoretical puzzle. It's a reminder of how much we still don't know about the universe. If such a galaxy exists, it could change everything we thought we knew about cosmology. It would challenge our understanding of why the universe looks the way it does and could open the door to new discoveries that go beyond even our wildest imagination. Whether we find an antimatter galaxy or not, the search itself is pushing the boundaries of science. Every experiment, every observation, and every theory brings us one step closer to understanding the deepest mysteries of the cosmos. And perhaps, one day, we'll finally have an answer to the question, could there be an antimatter galaxy out there, hiding just beyond our reach? The possibility of an antimatter galaxy hiding somewhere in the universe isn't just a theoretical curiosity. It's a fundamental question that could redefine our understanding of physics. If such a galaxy exists, it would mean that our universe is not entirely made of matter but instead consists of vast regions where antimatter thrives just as matter does in our own cosmic neighborhood. But if that's the case, why haven't we found one yet? And more importantly, what would happen if we did? One of the biggest challenges in identifying an antimatter galaxy is that, from a distance, it would look just like any other galaxy. Stars made of antimatter would shine just as brightly as stars made of matter, and the fundamental forces that govern stellar evolution would behave in the exact same way. There wouldn't be any immediate visual differences that would allow us to distinguish an antimatter galaxy from a regular one. This is because the laws of physics are symmetrical when it comes to matter and antimatter. An antimatter star would fuse antimatter atoms in its core the same way a normal star fuses hydrogen into helium. The only difference is that the antimatter star would be made of antimatter particles, antiprotons instead of protons, positrons instead of electrons. But because these particles behave just like their matter counterparts under the same conditions, the star would shine with the same kind of light, making it virtually impossible to detect using conventional telescopes. So how could we tell if a galaxy is made of antimatter? One way is by searching for the telltale signs of matter-antimatter annihilation. If an antimatter galaxy exists, there should be a boundary somewhere in the universe where matter and antimatter occasionally come into contact, producing high-energy gamma rays in the process. These gamma rays would be an unmistakable signature of annihilation. Scientists have looked for these gamma-ray signatures using space telescopes like the Fermi Gamma-Ray Space Telescope, which scans the universe for high-energy radiation. So far, no large-scale annihilation events have been detected, which suggests that if antimatter galaxies do exist, they must be located far away from matter-dominated regions of space. This supports the idea that if the universe does contain both matter and antimatter galaxies, they must be separated by vast cosmic voids, preventing them from interacting and destroying each other. But there's another way to search for antimatter galaxies, by detecting antimatter particles and cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, and some of them originate from outside our galaxy. If any of these particles are made of antimatter, specifically heavier antimatter elements like antihelium, it could be a sign that they came from an antimatter galaxy. The Alpha Magnetic Spectrometer, AMS-02, mounted on the International Space Station, is currently searching for these antimatter particles. In recent years, AMS-02 has reported possible detections of antihelium, which is exciting because antihelium is incredibly rare in our universe. If these detections are confirmed, they could provide the first direct evidence of antimatter regions in the cosmos. But if we do confirm the existence of an antimatter galaxy, what does that mean for our understanding of the universe? It could mean that matter and antimatter were naturally separated during the early moments of the Big Bang, rather than one being more dominant than the other. This would challenge the long-standing assumption that the universe must have been biased toward matter. Instead, it could mean that the universe developed in a way that allowed matter and antimatter to exist in separate domains, preventing total annihilation. This would also raise the possibility that the laws of physics might be different in antimatter regions of the universe. While our understanding of antimatter suggests that it should behave identically to matter, there could be subtle differences that we have yet to discover. If antimatter galaxies exist, they might hold clues about new physics that go beyond our current understanding of the Standard Model. And then there's the most fascinating question of all: could antimatter galaxies harbor life? If an antimatter galaxy exists, and if it contains planets made entirely of antimatter, then in theory, antimatter lifeforms could have evolved there just as they did in our own universe. These beings would be made of anti-atoms, forming anti-molecules, and ultimately, anti-biological systems that function just like ours. To them, their world would feel just as natural as ours does to us. They wouldn't perceive any difference, because all the fundamental interactions, gravity, electromagnetism, the strong and weak nuclear forces, would operate in the same way. But if an antimatter civilization ever attempted to communicate with us, the results would be catastrophic. Any physical contact between matter and antimatter would lead to complete annihilation, making direct interaction impossible. This could explain why we haven't encountered any signs of intelligent life from antimatter galaxies. If they exist, they may have discovered the dangers of traveling into matter-dominated regions long ago. Any attempt to cross into our part of the universe would be met with instant destruction, preventing any meaningful exploration or communication between our two realms. It also raises an eerie thought: what if we have already lost probes or spacecraft to an antimatter region without realizing it? If a spacecraft unknowingly entered an antimatter galaxy, it would be destroyed instantly upon contact with any antimatter particles. From our perspective, it would simply vanish, leaving no trace behind. Could this explain some of the mysterious disappearances of space probes that have been lost under unexplained circumstances? Probably not, but the idea is chilling nonetheless. This is why scientists are extremely careful when designing experiments to detect antimatter. If we were ever to collect antimatter from an antimatter galaxy and bring it back to Earth, it would need to be contained in a perfect vacuum, suspended by electromagnetic fields to prevent contact with matter. Any mistake would result in an explosion on an unimaginable scale. But despite these dangers, the search for an antimatter galaxy continues, because the implications are too important to ignore. Finding an antimatter galaxy would not only solve one of the biggest mysteries in physics but also provide new insights into the origins of the universe, the nature of space-time, and even the possibility of new energy sources that harness the unique properties of antimatter. If we do find evidence of an antimatter galaxy, it could lead to some of the most profound discoveries in the history of science. It would mean that the universe is far more complex than we ever imagined, with entire regions where antimatter thrives just as matter does here. It could even suggest that our universe is part of a larger cosmic structure where matter and antimatter exist in a delicate balance, separated by cosmic boundaries we have yet to understand. For now, the mystery remains unsolved. But as technology advances, and as we develop better ways to detect antimatter in space, we may one day uncover the truth. Could there be an antimatter galaxy hidden somewhere in the cosmos, waiting to be discovered? The answer could change everything we thought we knew about the universe. The idea that there could be entire galaxies made of antimatter is one of the most mind-bending possibilities in modern astrophysics. If such galaxies exist, they must be out there, hidden among the countless other galaxies we observe in the night sky. But if they are real, why haven't we detected them directly? Could they be more common than we think, just beyond the reach of our current technology? One of the biggest hurdles in detecting an antimatter galaxy is the fact that antimatter behaves almost identically to matter under normal circumstances. Light emitted by antimatter atoms would be indistinguishable from light emitted by normal atoms. This means that an antimatter galaxy could, in theory, be sitting right next to a matter galaxy, and we wouldn't even know it, unless they interacted in some way that produced a detectable signal. One possible way to find an antimatter galaxy is by searching for unusual gamma-ray emissions. When matter and antimatter come into contact, they annihilate each other in a burst of energy, producing highly energetic gamma rays. If an antimatter galaxy existed in a region of space where it occasionally came into contact with normal matter, we would expect to see bursts of gamma radiation from the boundary between the two regions. This is exactly what scientists have been looking for. The Fermi Gamma-Ray Space Telescope, one of the most powerful instruments ever built for detecting high-energy radiation, has scanned the sky for evidence of matter-antimatter annihilation events. However, despite years of observations, no clear evidence of large-scale annihilation has been found. This suggests that if antimatter galaxies exist, they must be isolated, separated from matter-dominated regions of space by vast cosmic voids that prevent them from interacting with normal galaxies. But what if antimatter galaxies don't interact with regular matter in the way we expect? What if there is some unknown force or hidden property of antimatter that prevents large-scale annihilation from occurring? This is one of the most intriguing possibilities, because it would imply that there is something about antimatter that we still don't fully understand. Our best understanding of antimatter comes from particle physics experiments, where antimatter particles are created in laboratories and studied under controlled conditions. In these experiments, antimatter behaves exactly as expected. When it comes into contact with normal matter, it annihilates immediately, releasing energy. This fundamental behavior is what makes antimatter such a powerful potential energy source. But it also makes it difficult to imagine how antimatter galaxies could exist without producing enormous amounts of detectable gamma radiation. Some physicists have speculated that there may be subtle differences between matter and antimatter that we have yet to discover. One possibility is that antimatter interacts with gravity differently than normal matter. In our universe, all matter is attracted to other matter through gravity, and antimatter is assumed to behave in the same way. But what if it doesn't? What if antimatter repels normal matter through some kind of anti-gravity effect? This idea, known as gravitational asymmetry, is still purely theoretical, but if true, it could help explain why we don't see massive annihilation events between matter and antimatter regions of space. If antimatter galaxies are repelled by normal matter, they could be pushed into isolated regions of the universe, preventing them from coming into contact with matter and making them extremely difficult to detect. Another possibility is that antimatter galaxies exist in a different phase of reality, one that we are not yet capable of perceiving. Some theories in quantum physics suggest that antimatter might have unique interactions with the fabric of space-time itself, making it behave in ways that are fundamentally different from matter. If this is the case, it's possible that antimatter galaxies could be hidden in plain sight, existing in a state that is invisible to our current instruments. This leads to another mind-boggling question. If antimatter galaxies exist, could they host antimatter life? The idea of antimatter lifeforms might sound like science fiction, but in principle, there is no reason why it couldn't be possible. If an antimatter galaxy follows the same physical laws as a matter galaxy, then antimatter planets could form, and those planets could develop conditions that support the formation of antimatter-based life. To an antimatter being, the universe would seem perfectly normal. Their chemistry would be based on antiatoms, which would form antimolecules, which would then build the structures of their bodies. Their version of biology would be completely consistent with the laws of physics as they experienced them. In fact, from their perspective, it would be our universe that seems strange and incompatible with life. But here's where things get really strange. If we ever encountered an antimatter civilization, it would be physically impossible to interact with them in a meaningful way. Any direct contact between matter and antimatter would result in instant annihilation, meaning that even the simplest handshake between a human and an antimatter being would release an explosion powerful enough to destroy a city. This raises a fascinating possibility. If intelligent life exists in antimatter galaxies, they might already be aware of us, but they would have no way to reach us without being destroyed in the process. Could this explain the apparent silence of the universe? If a significant portion of intelligent life exists in antimatter regions, it would mean that half of the universe's civilizations are effectively trapped in their own domains, unable to explore beyond their antimatter boundaries. There's also the unsettling thought that if an antimatter civilization developed advanced technology, they could, in theory, weaponize antimatter in ways we can't even imagine. Antimatter is the most energy-dense substance known to physics. If an antimatter civilization had the capability to store and manipulate antimatter in large quantities, they would possess a power that could make them one of the most formidable forces in the universe. Could an antimatter civilization one day figure out a way to interact with the matter universe without being annihilated? If so, how would they do it? Would they develop a way to contain matter within an antimatter-resistant field? Could they create artificial wormholes that allow information, but not physical objects, to pass between our universes? These are questions that remain purely speculative for now, but they highlight just how much we still don't understand about the nature of antimatter. Despite all these unknowns, the search for antimatter galaxies continues. The most promising way to find them might be through the detection of heavier antimatter elements, such as antihelium. The Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station has been searching for traces of antihelium in cosmic rays. If even a single atom of antihelium is detected, it would be one of the most groundbreaking discoveries in the history of physics, because it would strongly suggest that antimatter regions of the universe do exist. Some tantalizing hints have already emerged, with AMS-02 reporting possible detections of antihelium nuclei. However, these findings are still being analyzed, and scientists are being extremely cautious before making any definitive claims. If confirmed, these particles could have originated from an antimatter star, or even an entire antimatter galaxy, meaning that we may be on the verge of answering one of the greatest cosmic mysteries of all time. For now, the mystery remains unsolved. But as our technology improves, and as we develop new ways to detect antimatter in space, we may finally uncover the truth. If antimatter galaxies do exist, they could be some of the most extraordinary places in the universe. Hidden realms where the rules of physics are the same, yet everything is reversed. And if one day we do make contact, the consequences could change everything we know about our place in the cosmos. If antimatter galaxies exist, one of the biggest challenges we face is figuring out where they could be hiding. Space is unimaginably vast, with over 2 trillion galaxies in the observable universe, and each one could contain billions or even trillions of stars. That means even if antimatter galaxies are rare, they could still number in the millions or billions. The problem is, they would look almost identical to regular matter galaxies from a distance, making them nearly impossible to identify with our current telescopes. But there might be a way. One of the most promising methods for detecting an antimatter galaxy is by searching for signs of antimatter stars. Just like normal stars, antimatter stars would undergo nuclear fusion, converting antihydrogen into heavier antielements like antihelium and anticarbon. The light they emit would be almost indistinguishable from ordinary stars, but there could be subtle differences in their energy spectra that might reveal their true nature. The key would be to find stars that emit an unusual excess of high-energy radiation, which could be a clue that they are interacting with trace amounts of normal matter drifting through space. If even a small amount of interstellar matter from a neighboring galaxy were to fall into an antimatter star, the resulting annihilation would produce a burst of gamma rays unlike anything seen in a normal stellar environment. This means that by carefully studying unexplained gamma ray sources, we might be able to pinpoint the location of an antimatter star, and by extension, an antimatter galaxy. The search for such signals is already underway. The Fermi Gamma Ray Space Telescope has identified several mysterious high-energy sources that don't fit our current understanding of astrophysical objects. While none of them have been confirmed as antimatter stars yet, they remain intriguing candidates for further study. If even one of these sources turns out to be an antimatter star, it would be the first direct evidence that large-scale antimatter structures exist in the universe. But let's take this a step further. What if antimatter galaxies are not just isolated anomalies, but a fundamental part of the cosmic structure? Some physicists have proposed that the universe might be divided into massive regions of matter and antimatter, separated by cosmic voids that prevent them from coming into contact. If this is the case, then the observable universe as we know it might be just one half of a much larger, symmetric cosmos, with antimatter galaxies forming their own vast networks beyond the reach of our telescopes. This idea is closely related to the concept of baryon symmetry, which suggests that for every particle of matter created during the Big Bang, an equal amount of antimatter should have been produced. The fact that we don't see large amounts of antimatter in our local universe is one of the biggest unsolved mysteries in physics. Most scientists believe that some unknown process must have caused a tiny imbalance in the early universe, leading to the dominance of matter over antimatter. But if antimatter galaxies exist, it could mean that the imbalance was not as extreme as we thought. It could simply be that antimatter ended up in a different part of the universe, far from where we can easily detect it. If true, this would have profound implications for our understanding of cosmic evolution. It would mean that the universe is not as asymmetrical as it appears, and that antimatter galaxies could be just as common as matter galaxies, but distributed in a way that keeps them hidden from us. This could also mean that there are entire superclusters of antimatter galaxies, forming vast cosmic structures that mirror the matter-based structures we see in the observable universe. But if these antimatter regions exist, how did they form? One possibility is that the early universe underwent a phase transition, similar to the way water freezes into ice. During this transition, regions of space may have spontaneously separated into matter-dominated and antimatter-dominated zones, like oil and water refusing to mix. This would have created natural boundaries between the two regions, preventing large-scale annihilation and allowing both matter and antimatter galaxies to evolve independently. Another possibility is that antimatter galaxies formed in regions where the density fluctuations in the early universe favored antimatter over matter. The cosmic microwave background radiation, the afterglow of the Big Bang, shows that the early universe was not perfectly uniform, but had tiny variations in density. If some of these high-density regions contained more antimatter than matter, they could have evolved into antimatter galaxies while the surrounding regions became matter-dominated. This raises another fascinating question: could there be entire antimatter galaxy clusters? If individual antimatter galaxies exist, then there's no reason why they couldn't group together to form massive structures, just like normal galaxies do. Antimatter superclusters, stretching across millions of light-years, could be hidden in the far reaches of the universe, beyond the limits of our current observational technology. One of the most extreme possibilities is that the universe is structured in a way that matter and antimatter galaxies exist in a checkerboard-like pattern, separated by enormous voids that prevent them from interacting. If this were the case, then for every matter-dominated region of the universe we observe, there could be a corresponding antimatter region just out of reach. This would mean that the true scale of the universe is far larger than we ever imagined, with a perfectly balanced distribution of matter and antimatter across the cosmos. But what would it mean if we actually discovered an antimatter galaxy? The implications would be staggering. It would challenge our fundamental understanding of cosmology, forcing us to rethink everything we know about how the universe evolved. It could also open up entirely new possibilities for space travel, energy production, and even intergalactic communication. For example, if we could find a way to safely harvest antimatter from an antimatter galaxy, it could revolutionize space propulsion. Antimatter-matter annihilation is the most efficient energy release mechanism known to science, producing 100% energy conversion with no residual waste. This means that an antimatter-based spacecraft could achieve speeds far beyond anything possible with conventional rocket technology, potentially reaching a significant fraction of the speed of light. However, the dangers of interacting with an antimatter galaxy cannot be overstated. If even a small amount of normal matter were to accidentally come into contact with an antimatter world, the resulting explosion would be catastrophic. This means that any attempt to explore an antimatter galaxy would require unprecedented levels of precision and control to prevent unintended annihilation events. But beyond the practical challenges, the discovery of an antimatter galaxy would also have profound philosophical and existential implications. It would raise fundamental questions about the nature of the universe and our place in it. Are we truly alone, or is there an entire antimatter civilization out there, looking up at their night sky and wondering the same thing? If intelligent life exists in an antimatter galaxy, they might have their own theories about the nature of the universe. They might have their own version of physics, their own scientific discoveries, and their own attempts to understand the cosmos. But unless they have found a way to safely interact with the matter universe, they would remain forever isolated, unable to reach us without risking total annihilation. This raises another mind-blowing possibility. What if we have already detected signs of an antimatter civilization, but we simply didn't recognize them for what they were? Could some of the unexplained signals detected by our telescopes be attempts at communication from an antimatter world? If so, how would we even begin to understand them? The mystery of antimatter galaxies is one of the greatest unsolved questions in modern astrophysics. Despite decades of research, we are still left with more questions than answers. But as technology advances, and as new observational techniques are developed, we may be on the verge of unlocking one of the deepest secrets of the cosmos. For now, we can only wonder what might be out there, hidden among the stars. But one thing is certain: the universe is far stranger than we ever imagined, and the truth may be waiting for us in the most unexpected places. One of the biggest challenges in proving the existence of antimatter galaxies is that, from a purely observational standpoint, they would look nearly identical to regular galaxies. If you were to look at an antimatter galaxy through a telescope, it would have the same glowing clusters of stars, the same swirling clouds of gas, and the same vast cosmic structures that we see in matter-based galaxies. The electromagnetic radiation emitted by antimatter behaves exactly like that from normal matter, which means that a distant observer would have no obvious way of distinguishing between the two. So how could we detect them? Scientists have proposed several indirect methods that could reveal the presence of antimatter galaxies. One of the most promising approaches involves searching for the unique signatures of matter-antimatter annihilation. If there is even a small amount of mixing between matter and antimatter in intergalactic space, we should be able to detect gamma rays produced by these annihilation events. In theory, if an antimatter galaxy existed near a normal matter galaxy, we would expect to see a boundary where small amounts of matter and antimatter occasionally come into contact. The resulting annihilation would generate high-energy gamma-ray bursts, which could serve as a telltale sign that an antimatter galaxy is present. However, despite decades of searching, astronomers have not yet found clear evidence of such large-scale annihilation events. This has led some scientists to propose that if antimatter galaxies do exist, they must be located in regions of the universe that are completely isolated from normal matter. These regions could be separated by immense cosmic voids, preventing any interaction between matter and antimatter on a scale large enough to be detectable. This would explain why we don't see widespread annihilation events lighting up the cosmos. But even if antimatter galaxies are hidden away in remote regions of the universe, there may still be a way to detect them. One possibility is that antimatter stars might produce subtle differences in their spectra compared to normal stars. These differences could arise due to the way antimatter interacts with radiation, or because antimatter stars might form differently from regular stars due to the properties of antielements. By carefully analyzing the light from distant galaxies, astronomers may one day be able to find these tiny spectral clues that reveal the presence of antimatter. Another possible approach is to search for antimatter cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. If antimatter galaxies exist, they should occasionally send out antimatter cosmic rays that could be detected here on Earth. In fact, some experiments have already detected rare antihelium nuclei in cosmic rays, something that is difficult to explain if all of the universe is made of matter. If future observations confirm the presence of antimatter cosmic rays, it could be strong evidence that antimatter galaxies are out there. But what if we take this idea even further? What if entire antimatter galaxy clusters exist, stretching across millions of light years? If antimatter galaxies exist in isolation, there's no reason they couldn't form their own vast cosmic structures, just like normal galaxies do. In this case, we might be looking at a universe where matter and antimatter are not just coexisting, but actually forming two parallel cosmic networks, each evolving independently. This idea leads to some fascinating possibilities. Could there be entire antimatter superclusters? Could there be antimatter quasars, where supermassive black holes at the centers of antimatter galaxies are feeding on antimatter gas, just like normal quasars do? If so, these antimatter quasars might produce slightly different signals compared to their matter-based counterparts, giving us another possible way to detect them. If antimatter galaxies exist, then we have to ask, what does this mean for our understanding of the universe? The discovery of even a single antimatter galaxy would force us to completely rethink the standard model of cosmology. It would suggest that the imbalance of matter and antimatter in the universe is not as extreme as we once thought, and that antimatter may have simply ended up in regions we haven't explored yet. But if this is the case, then where does that leave us? Could our own galaxy be surrounded by antimatter galaxies that are just too far away to interact with? Could there be an entire antimatter version of the Milky Way somewhere in the universe, with its own antimatter planets, antimatter stars, and possibly even antimatter life? This is where the mystery gets even deeper. If life can exist in an antimatter galaxy, would it be fundamentally different from life as we know it? Or would the laws of physics allow for antimatter-based organisms that function in the same way as regular life? Some scientists believe that, in theory, an antimatter civilization could evolve just like a matter-based one. If the chemistry of antimatter behaves the same way as normal chemistry, then antimatter molecules could form complex structures, leading to the possibility of antimatter-based biology. This leads to one of the most mind-blowing questions of all. Could we ever make contact with an antimatter civilization? If intelligent beings exist in an antimatter galaxy, would they be able to detect our universe? If they did, how would they react? There's one major problem. Direct interaction between a matter civilization and an antimatter civilization would be almost impossible. If even a small amount of matter from our universe came into contact with their world, the resulting annihilation would be catastrophic. This means that if an antimatter civilization exists, they might have discovered our universe but realized that any attempt to reach us would be too dangerous. But what if they found a way? Could an advanced civilization develop technology to interact with our universe safely? Some scientists have speculated about the possibility of using electromagnetic forces to create a barrier between matter and antimatter, preventing annihilation. If such technology is possible, then in the distant future, matter and antimatter civilizations might find a way to communicate, or even collaborate without destroying each other. This raises another fascinating question. Could some of the unexplained cosmic signals we detect be from an antimatter civilization trying to reach out? Could mysterious radio bursts or high-energy signals be attempts at interuniversal communication? If an antimatter civilization has been studying our universe, they might have already found a way to send messages in a form that we don't yet recognize. As we continue searching for answers, the possibility of antimatter galaxies remains one of the greatest unsolved mysteries of modern physics. The universe is filled with unknowns, and antimatter could be the key to unlocking some of its deepest secrets. Whether we discover an antimatter galaxy next year, in 100 years, or never at all, the search itself is pushing the boundaries of our understanding and bringing us closer to answering some of the biggest questions in science. For now, we can only look up at the stars and wonder, what else is out there? Could there be an antimatter version of our own galaxy, waiting to be discovered? And if so, what incredible discoveries still await us in the vast, unexplored cosmos? If an antimatter galaxy does exist, the consequences would be profound, not just for astrophysics, but for our entire understanding of the cosmos. Right now, the leading theory in physics suggests that our universe is overwhelmingly made of matter, with only tiny amounts of antimatter scattered throughout. This assumption is based on what we can observe. But if an entire antimatter galaxy, or even an antimatter supercluster, exists, then we have to ask, how did it form? And why hasn't it been annihilated by regular matter? This brings us back to the fundamental question. Why does the universe seem to have more matter than antimatter in the first place? According to the Big Bang theory, the early universe should have created equal amounts of both. But if that were the case, then nearly all of it should have annihilated, leaving behind only energy. Yet, here we are, living in a universe that is clearly dominated by matter. One possibility is that the imbalance was caused by a tiny difference in the way matter and antimatter behave. This is called CP violation, and it's been observed in particle physics experiments. Essentially, it means that under certain conditions, the laws of physics don't treat matter and antimatter as exact mirror images. If this asymmetry existed in the early universe, it could explain why matter ended up dominating over antimatter. But what if there wasn't an imbalance at all? What if, instead of one universe made mostly of matter, the cosmos naturally sorted matter and antimatter into separate regions? In other words, rather than annihilating completely, matter and antimatter could have been pushed apart into different cosmic structures during the early stages of the universe. This idea has led some scientists to propose the existence of a baryogenesis process that might have separated matter and antimatter into different domains. In this scenario, the universe could contain vast pockets of antimatter galaxies that have remained isolated from matter for billions of years. If this is true, then entire antimatter superclusters could be out there, hidden beyond the reach of our current observations. One of the biggest challenges in proving this theory is that, as we mentioned earlier, antimatter galaxies would look almost exactly like normal galaxies. The light they emit would be indistinguishable because photons, particles of light, are their own antiparticles. This means that even if we pointed our most powerful telescopes at an antimatter galaxy, we wouldn't immediately be able to tell the difference. So how could we confirm the existence of an antimatter galaxy? One way would be to look for rare annihilation signals at the edges of cosmic structures. If an antimatter galaxy were near a region of normal matter, some intergalactic gas should occasionally drift between the two. When this happens, it would result in high-energy gamma-ray bursts from matter-antimatter annihilation. Astronomers have searched for these signals, and while some unexplained gamma-ray sources have been detected, none have definitively been linked to large-scale matter-antimatter interactions. This suggests that if antimatter galaxies exist, they must be extremely isolated from normal matter. Another possible method for detection is studying cosmic rays. If antimatter galaxies exist, then some antimatter particles, such as antihelium nuclei, should be floating through space. In recent years, scientists have detected rare hints of these particles in cosmic ray experiments. While these findings are still inconclusive, they raise the possibility that antimatter regions of the universe might exist after all. But let's take this one step further. If antimatter galaxies exist, then could they have their own planetary systems? Their own antimatter stars, antimatter planets, and possibly even antimatter life? In theory, antimatter atoms should behave just like regular atoms, forming molecules, chemical reactions, and even biological structures. If an antimatter Earth existed in an antimatter galaxy, it could have undergone the same evolutionary processes that led to life here. This means that, somewhere out there, an antimatter civilization could be looking up at their sky, wondering if they are alone, just as we do. But here's where things get really strange. If an antimatter civilization developed advanced technology, they might have discovered our matter-based universe. If they attempted to explore it, however, they would face an enormous problem. Direct contact with our universe would lead to instant annihilation. This raises an even bigger question. Could an antimatter civilization have already tried to communicate with us? Could some of the strange, unexplained signals we detect in space, such as fast radio bursts, actually be attempts from an antimatter intelligence to reach out in a way that doesn't result in mutual destruction? There's also the possibility that, if antimatter galaxies exist, they could contain completely different physics. While we assume antimatter behaves exactly like matter in all respects, there could be unknown differences that change the way antimatter galaxies evolve. Could antimatter have its own unique physical laws? Could antimatter black holes behave differently from regular black holes? Could antimatter planets experience time in a different way? If antimatter galaxies exist, then they would represent an entire parallel version of the universe, one that we are just beginning to consider. The discovery of even a single antimatter galaxy would revolutionize everything we know about physics, cosmology, and the structure of reality itself. For now, the search continues. Astronomers are pushing the boundaries of observation, designing new experiments, and looking for the smallest hints that could reveal the presence of antimatter galaxies. As our technology improves, we may one day have the ability to detect antimatter structures in ways we can't yet imagine. And when that day comes, we might finally have an answer to one of the biggest questions in cosmology. Are we living in a universe of matter, or are we simply one half of a grand cosmic balance, with an entire antimatter cosmos waiting to be discovered? If an antimatter galaxy exists, it could challenge our most fundamental assumptions about how the universe formed and evolved. Right now, the standard model of cosmology tells us that the universe began with a nearly uniform distribution of matter and radiation. Over time, gravity pulled matter together, forming galaxies, stars, and planets. But if some regions of the universe are entirely made of antimatter, this means there must have been some unknown mechanism that separated matter from antimatter in the early universe. One possibility is that space itself has vast cosmic domains where matter and antimatter were naturally divided. Some theorists propose that the inflationary period, the rapid expansion of the universe in its earliest moments, could have stretched out these domains to enormous scales, making antimatter galaxies extremely rare but not impossible. This would mean that we don't see antimatter galaxies nearby simply because the universe naturally structured itself in a way that kept them far apart from matter-based galaxies like our own. But if that's the case, how would such an antimatter galaxy sustain itself over billions of years? If an antimatter galaxy were surrounded by normal galaxies, we would expect to see massive regions of annihilation where matter and antimatter collide. Yet, when we look at the cosmos, we don't see widespread gamma-ray emissions at the levels we would expect if this were happening on a large scale. This suggests that if antimatter galaxies do exist, they must be incredibly isolated. The search for antimatter galaxies has led astronomers to examine some of the most distant and mysterious cosmic objects, quasars. Quasars are extremely bright and energetic, powered by supermassive black holes consuming material at their centers. Some researchers have wondered if certain quasars could be the result of antimatter-matter interactions, producing excess gamma-ray radiation. However, so far, observations have not provided conclusive evidence of antimatter-based quasars. Another challenge in detecting antimatter galaxies is that antimatter behaves exactly like normal matter when it comes to light emission. The laws of physics tell us that an antimatter hydrogen atom, for example, would absorb and emit photons in the same way that a normal hydrogen atom does. This makes it nearly impossible to distinguish an antimatter galaxy from a regular matter-based galaxy using optical telescopes alone. So if we can't see antimatter galaxies directly, and we don't observe massive annihilation events that would prove their existence, what else can we do? One promising method involves searching for cosmic rays that contain antimatter elements that should not exist in our matter-dominated universe. The Alpha Magnetic Spectrometer, AMS-02, a particle detector mounted on the International Space Station, has been collecting data on high-energy cosmic rays for over a decade. Among the many particles it has detected, scientists have found rare hints of antihelium nuclei. If confirmed, this would be groundbreaking, because antihelium is not something that should naturally form in our matter-dominated universe. Its presence would strongly suggest that there are regions of the universe where antimatter still exists in significant amounts, perhaps entire antimatter star systems, or even galaxies. But there's still another mind-boggling question to consider. If antimatter galaxies exist, could they have their own unique physics? Right now, we assume that antimatter follows the exact same physical laws as regular matter. But what if that assumption is wrong? One of the biggest mysteries in modern physics is gravity. We know that matter is affected by gravity, but we have never directly observed how antimatter behaves in a gravitational field. Some experiments suggest that antimatter should fall downwards just like normal matter, but there are theoretical possibilities that antimatter could interact with gravity in a different way. If that's the case, then an antimatter galaxy could have unusual gravitational effects that don't match our current models. Could antimatter galaxies have different structures than regular galaxies? Could their black holes behave differently? Could an antimatter universe expand at a different rate than ours? These questions push the boundaries of our understanding, and finding the answers could lead to the discovery of entirely new physics. But here's an even wilder idea. What if the presence of an antimatter galaxy means that our universe is actually part of a much larger, balanced system? Some physicists have proposed that our universe could be just one half of a greater reality, with a mirror version of the cosmos composed entirely of antimatter. This twin universe could be connected to ours through some unknown mechanism, perhaps through cosmic strings, extra dimensions, or even a fundamental symmetry in the fabric of reality. If such a mirror universe exists, then what we perceive as empty space might actually be a boundary between two cosmic domains, one of matter and one of antimatter. Could there be some yet undiscovered force that keeps these two regions separated, preventing them from annihilating? Could dark energy, the mysterious force driving the accelerated expansion of the universe, be related to the interaction between matter and antimatter on a cosmic scale? And what about intelligent life? If an antimatter galaxy exists, then it stands to reason that antimatter planets could form, and if the conditions are right, life could emerge. Would an antimatter civilization ever be able to communicate with us? Or would the physical barrier between matter and antimatter make direct contact impossible? Imagine if an antimatter alien civilization developed advanced space travel and sent probes toward our galaxy. The moment one of their spacecraft entered our region of space, it would be instantly annihilated upon contact with normal matter, releasing an enormous burst of energy. This means that an antimatter civilization might already know about us but could have no safe way to approach us. And here's something to think about. What if the reason we haven't seen direct evidence of antimatter galaxies is because they are avoiding us? If an antimatter civilization understands the dangers of interacting with a matter-based universe, they might have developed ways to stay hidden, using advanced technology to minimize their interactions with our universe. Or perhaps they are actively studying us from afar, trying to find a way to bridge the divide between matter and antimatter without destruction. Could some of the mysterious signals we detect from deep space, such as fast radio bursts, be attempts from an antimatter civilization to communicate without annihilation? At this point, the mystery of antimatter galaxies is one of the greatest unknowns in astrophysics. If even one antimatter galaxy is found, it would challenge everything we thought we knew about the structure of the universe. It would mean that the cosmos is far more complex than we ever imagined, with entire regions operating under different conditions than our own. The search continues, and with each new scientific breakthrough, we get closer to uncovering the truth. Whether through deep space observations, cosmic ray detections, or new physics experiments, we may one day confirm that antimatter galaxies are not just a theoretical possibility but a reality hidden in the vastness of the universe. And when that day comes, it will not just be a scientific discovery, it will be a revelation that reshapes our place in the cosmos forever. The search for antimatter galaxies continues, but the deeper we dig into the mystery, the more it challenges our fundamental understanding of the universe. If an antimatter galaxy does exist somewhere in the cosmos, how did it form, and why did it remain separate from the vast regions dominated by normal matter? Could there be entire antimatter clusters or even superclusters, completely hidden from us except for rare cosmic clues? To understand the stakes, let's take a step back and think about why this mystery is so baffling. Our current models of physics tell us that the Big Bang should have created equal amounts of matter and antimatter. But when we look around, the observable universe is almost entirely made of matter. If antimatter galaxies exist, it means that instead of all the antimatter being annihilated in the early universe, some of it must have survived, somehow forming structures that are still intact today. This raises massive questions about how the laws of physics operated in the first moments after the Big Bang. One of the biggest problems in physics is something called the baryon asymmetry problem. This is the mystery of why the universe ended up with far more matter than antimatter. If nature were perfectly symmetrical, every particle of matter should have had an equal counterpart of antimatter, and they should have annihilated each other completely, leaving behind a universe filled with nothing but energy. But that didn't happen. Instead, matter won. Or at least that's what we assume, because we haven't found an antimatter galaxy yet. But what if there are hidden antimatter galaxies, completely separated from our own? One theory suggests that vast cosmic voids, empty regions of space between galaxy clusters, could be the dividing lines between matter and antimatter domains. If antimatter galaxies exist, they would need to be incredibly distant from normal galaxies to avoid catastrophic annihilation at the boundaries where the two meet. The problem is that voids in the cosmic web are immense. Some of them stretch for hundreds of millions of light years across, and if antimatter galaxies are isolated inside these voids, they would be extremely difficult to detect. Normal galaxies are already hard to see at extreme distances, and an antimatter galaxy would look identical to a matter galaxy in most wavelengths of light. This means that even if our telescopes are already capturing light from an antimatter galaxy, we wouldn't be able to tell the difference just by looking at it. But there's another way we might find them, by looking for the unique cosmic rays that antimatter galaxies should produce. When high-energy particles collide in space, they sometimes create pairs of matter and antimatter particles. However, if entire antimatter stars exist, they should produce antimatter elements that don't naturally form in our matter-dominated universe. In 2018, the Alpha Magnetic Spectrometer, AMS-02, detected possible antihelium particles in cosmic rays, something that shouldn't exist unless antimatter stars or galaxies are out there somewhere. If these detections are confirmed, they could be the first direct evidence that antimatter structures exist beyond the occasional particle collisions we observe in space. So, if an antimatter galaxy does exist, what does that mean for our understanding of physics? Right now, one of the most important principles in modern physics is something called CPT symmetry, charge, parity, and time symmetry. This principle states that the fundamental laws of physics should remain the same if we swap matter for antimatter, charge, flip the universe as if it were in a mirror, parity, and reverse the flow of time. If antimatter galaxies exist, they might be key to testing whether this symmetry holds at the largest cosmic scales. Could antimatter galaxies obey slightly different physical laws than our own? Could they have unique gravitational effects, or could time itself behave differently in these regions? These questions go far beyond astrophysics. They could reshape everything we know about the nature of reality. One of the most radical theories suggests that an antimatter universe might exist parallel to our own, connected in ways we don't yet understand. Some physicists propose that dark energy, the mysterious force causing the universe to expand faster and faster, could actually be the result of interactions between matter and antimatter on a cosmic scale. If an antimatter galaxy is out there, could it be influencing our own universe in ways we've never considered? And then there's the question of life. If antimatter galaxies exist, could they have antimatter planets with antimatter life? If such a civilization evolved, would they have discovered the existence of our matter universe? If they tried to explore beyond their galaxy, they would face the same problem we would: instant annihilation upon contact with normal matter. But what if they found a way around this? Could an antimatter civilization develop technology that allows them to observe us from afar? Could they send signals or probes made of something other than matter or antimatter? Perhaps some unknown form of neutral energy? And here's another mind-bending thought. What if they've already tried? What if some of the unexplained cosmic signals we've detected, like fast radio bursts, are actually attempts at communication from an antimatter civilization? If they know about us, and they understand the risks of contact, their only option might be to send signals in a way that doesn't involve physical matter at all. The mystery of antimatter galaxies isn't just about astronomy, it's about the fundamental nature of the universe itself. If we discover even one antimatter galaxy, it will mean that our entire understanding of cosmic evolution is incomplete. It will mean that the universe is far stranger than we ever imagined, with vast, hidden regions where the laws of physics might not be exactly what we think they are. The search continues, and with every new observation, we get one step closer to finding the truth. Could there be an antimatter galaxy somewhere out there, waiting to be discovered? The answer could change everything. If an antimatter galaxy is out there, its existence would raise profound questions about how the universe formed and evolved. It would mean that at least some regions of space followed a vastly different path after the Big Bang, one where antimatter somehow avoided annihilation and was able to form stable structures like stars, planets, and perhaps even life. But how would such a galaxy remain hidden for so long? Wouldn't we have seen some kind of evidence by now? One major reason we haven't found an antimatter galaxy yet is that it would look almost exactly like a regular matter galaxy. If you placed an antimatter galaxy right next to a normal one and observed them from millions of light years away, they would be indistinguishable in terms of brightness, shape, and even their spectral signatures. The light emitted by antimatter atoms would behave the same way as light from normal matter. This means that even if we have already captured images of an antimatter galaxy, we wouldn't recognize it as anything special just by looking at it. However, there's one way we might detect the presence of an antimatter galaxy: by searching for the deadly boundary where antimatter meets matter. If an antimatter galaxy existed near a normal matter galaxy, there would be a region where the two kinds of matter interact. At this boundary, hydrogen from one galaxy would collide with antihydrogen from the other, releasing massive amounts of gamma radiation. This annihilation process would be incredibly energetic, producing signals far stronger than typical cosmic events. But so far, astronomers have not observed any large-scale gamma-ray emissions that would suggest a cosmic-scale matter-antimatter interaction. This suggests one of two possibilities. Either antimatter galaxies do not exist in our observable universe, or they are so far away, perhaps even beyond the cosmic horizon, that their light has not yet reached us. If an antimatter galaxy does exist, it might be located in a completely separate region of the universe, isolated from matter galaxies by enormous voids of empty space. There's another strange possibility to consider. What if antimatter galaxies exist, but they behave differently than we expect? Some physicists speculate that antimatter might interact with gravity in an unusual way. In our universe, all matter is attracted to other matter due to gravity. But what if antimatter repelled normal matter instead of attracting it? This concept is known as gravitational repulsion, and while there is no direct evidence for it, some theories suggest that antimatter galaxies could be pushed away from matter galaxies due to this effect, making them even harder to detect. The idea of gravitational repulsion has massive implications for our understanding of physics. If antimatter galaxies have a unique relationship with gravity, it could help explain some of the greatest mysteries in cosmology, such as the accelerated expansion of the universe. Right now, scientists believe that dark energy is responsible for this acceleration. But what if the expansion of the universe is actually being influenced by vast, hidden antimatter regions that are repelling normal matter? If this is true, it means that antimatter galaxies might not just exist, they might be actively shaping the universe on a cosmic scale. The unseen influence of antimatter galaxies could be stretching space itself, subtly altering the movement of galaxy clusters and even affecting the way time flows across different regions of the universe. But there's an even stranger possibility. What if the reason we haven't found antimatter galaxies is that we're looking in the wrong way? We assume that antimatter galaxies would exist in the same kind of universe we do, with stars and planets made of antimatter behaving just like their matter counterparts. But what if antimatter galaxies are governed by completely different laws of physics? Some radical theories suggest that antimatter might not interact with light in the same way that normal matter does. If this is true, then an antimatter galaxy might be completely invisible to us, not because it is far away, but because its very nature prevents it from emitting or reflecting light in a way we can detect. This could mean that entire antimatter structures exist right next to normal matter galaxies, hidden in a way that makes them undetectable with our current technology. If this is the case, how could we ever find them? One way might be to look for indirect effects, such as the gravitational influence of an unseen antimatter galaxy on surrounding matter galaxies. If an antimatter galaxy were nearby, its gravitational pull should affect the movement of visible galaxies around it. If astronomers detect unexplained gravitational anomalies, regions of space where galaxies move in unexpected ways, it could be a clue that an invisible antimatter structure is lurking nearby. Another possibility is that antimatter galaxies might emit unknown particles that we haven't identified yet. Current experiments, such as those at CERN, are studying the fundamental properties of antimatter to determine if it has any unique signatures that could be used to identify antimatter structures in space. If scientists discover that antimatter produces a unique type of radiation or particle, we could build detectors specifically designed to search for these signals across the cosmos. But there's one final, mind-bending idea to consider. What if our own universe is just one side of a larger, mirror-image reality? Some theories suggest that the universe might have an equal and opposite counterpart, a parallel cosmos composed entirely of antimatter. In this scenario, what we call dark energy might actually be the gravitational pull of an entire antimatter universe interacting with our own in ways we don't yet understand. If this is true, then antimatter galaxies might not be part of our observable universe at all. Instead, they might exist in a separate dimension, linked to our own through hidden cosmic forces that we have yet to discover. This could explain why the universe appears to be expanding faster than expected, because it is being influenced by a massive, invisible antimatter counterpart. The search for antimatter galaxies is not just about finding exotic forms of matter, it's about unlocking the deepest secrets of the cosmos. If an antimatter galaxy exists, it would challenge everything we know about physics, from the nature of gravity to the ultimate fate of the universe. It would force us to rethink the very fabric of reality, leading to discoveries that could change our understanding of space, time, and even the possibility of other universes. So, could an antimatter galaxy be out there, waiting to be discovered? The answer may be closer than we think, or it may be hidden in ways we can't yet comprehend. The only certainty is that the universe is far more mysterious than we ever imagined, and the search for antimatter galaxies is only just beginning. The search for antimatter galaxies forces us to confront some of the deepest mysteries in physics. If an entire galaxy made of antimatter exists, it would mean that our current understanding of the universe is incomplete. It would suggest that there are vast, hidden regions of space where antimatter has somehow survived since the Big Bang, defying the expectation that it should have been annihilated long ago. But if these galaxies exist, how did they come to be? And why haven't we found any clear evidence of them? One of the most puzzling questions is how antimatter galaxies could have formed in the first place. According to the standard model of cosmology, the universe began as a hot, dense state where matter and antimatter should have been created in equal amounts. But if this were true, they should have annihilated each other completely, leaving behind nothing but energy. And yet, our universe is filled with normal matter, with almost no antimatter to be found. This suggests that something happened in the early universe that caused a tiny imbalance, an asymmetry that allowed matter to dominate over antimatter. Scientists have proposed various mechanisms to explain this imbalance, but none of them fully account for why antimatter seems to have almost completely disappeared. One possibility is that instead of being entirely annihilated, antimatter was somehow separated from normal matter in the early universe, forming its own isolated regions. If this happened, it could mean that entire clusters of galaxies exist beyond our reach, composed entirely of antimatter. But how could such a separation have occurred? One theory suggests that quantum fluctuations in the early universe might have created regions where antimatter was more concentrated than matter. If these regions expanded and became gravitationally bound, they could have evolved into antimatter galaxies, completely cut off from the matter-dominated regions of the universe. Another idea is that a fundamental force, beyond the four known forces of nature, may have pushed matter and antimatter apart on a cosmic scale, keeping them from interacting and annihilating each other. If such antimatter regions exist, they would be completely stable as long as they remain isolated from normal matter. An antimatter galaxy would have antimatter stars, antimatter planets, and even antimatter black holes, all behaving exactly like their matter counterparts. From a distance, they would look indistinguishable from normal galaxies, making them incredibly difficult to detect. But there are still ways we might be able to find them. One potential method is through cosmic ray detection. When high-energy particles travel through space, they sometimes collide with interstellar matter, producing secondary particles. If we were to detect an unusually high number of positrons, antimatter electrons, in cosmic rays, it could be a sign that antimatter structures exist somewhere in the universe. In fact, some experiments, such as those conducted by the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station, have detected an excess of positrons that cannot yet be fully explained. Some scientists speculate that this could be a hint of antimatter galaxies, though alternative explanations, such as dark matter interactions, are also possible. Another way to search for antimatter galaxies is by looking at the cosmic microwave background radiation, the faint glow left over from the Big Bang. If large-scale antimatter regions exist, they could leave subtle imprints on this radiation, creating anomalies in its temperature and polarization patterns. Researchers are currently analyzing data from missions like the Planck satellite to search for these potential signatures. But perhaps the most promising method for detecting antimatter galaxies is through advanced gamma-ray telescopes. If an antimatter galaxy were to interact with even a small amount of normal matter, it would produce intense bursts of gamma rays from annihilation events. By scanning the sky for unexplained gamma-ray sources, astronomers might be able to identify regions where antimatter could be present. Future space observatories, equipped with next-generation gamma-ray detectors, could play a crucial role in this search. If we do find an antimatter galaxy, it would be one of the most groundbreaking discoveries in the history of science. It would confirm that the universe is far stranger than we ever imagined and would force us to rethink fundamental theories about the nature of matter and antimatter. But beyond the scientific implications, the existence of antimatter galaxies raises an even more intriguing question. Could there be antimatter life? If antimatter galaxies exist, it's possible that they have evolved in the same way that matter galaxies have. That means they could have antimatter stars with habitable antimatter planets orbiting them. And if the conditions on these planets are similar to those on Earth, could there be living organisms made entirely of antimatter? Theoretically, an antimatter civilization could exist somewhere in an antimatter galaxy, completely unaware of the matter-dominated universe beyond its cosmic horizon. But what would happen if we ever made contact with such a civilization? If a spacecraft from a matter-based civilization were to land on an antimatter planet, the result would be catastrophic. The moment matter and antimatter came into contact, they would annihilate each other in a massive explosion, releasing pure energy. Even a single handshake between a human and an antimatter being would result in complete annihilation. This makes the idea of direct interaction nearly impossible, unless there is some unknown force keeping matter and antimatter apart. The more we explore the universe, the more we realize how much we still don't know. The question of whether antimatter galaxies exist is not just about finding a new type of celestial object, it's about understanding the very fabric of reality. If we discover even a single antimatter galaxy, it would change our understanding of physics, cosmology, and even the ultimate fate of the universe. Could an antimatter galaxy be hidden somewhere, waiting to be discovered? Could there be entire antimatter civilizations out there, separated from us by nothing more than the fundamental laws of physics? The search for answers continues, and as our technology improves, we may one day uncover the truth. But for now, the mystery remains unsolved, leaving us to wonder what strange and unimaginable things might be lurking in the depths of space. The possibility of antimatter galaxies presents one of the most profound and unsettling mysteries in modern astrophysics. If such galaxies exist, they challenge our fundamental understanding of the universe and force us to reconsider the laws that govern reality. But if we accept that entire galaxies of antimatter could be hidden somewhere in the cosmos, we must ask an even bigger question. What does this mean for the structure of the universe itself? Could the cosmos be divided into separate domains, one dominated by matter, the other by antimatter, existing in delicate isolation to avoid catastrophic annihilation? If there are antimatter galaxies, they must exist in regions where they never come into contact with normal matter. This suggests that the universe might be structured in a way that naturally separates matter and antimatter on the largest scales. Some cosmologists have proposed that the early universe may have undergone a process that segregated matter and antimatter into different cosmic regions, possibly due to some unknown force acting at the moment of the Big Bang. This would mean that antimatter galaxies aren't just random anomalies, but are instead part of a much larger, hidden structure within the universe. But if such a structure exists, how can we detect it? One potential clue lies in the cosmic voids, vast empty regions between galaxy clusters. These voids appear to be largely devoid of normal matter, raising the possibility that some of them might actually contain antimatter galaxies that are invisible to us. If an antimatter galaxy were located in one of these voids, it could remain undetected for billions of years simply because it never encounters normal matter. However, if even the smallest trace of normal matter were to drift into an antimatter galaxy, the resulting annihilation would produce detectable gamma rays. This means that carefully studying the edges of cosmic voids with high-energy telescopes could be a way to find hidden antimatter structures. Another possibility is that antimatter galaxies might not be evenly distributed throughout the universe. Instead, they could exist in specific regions where conditions were different during the early expansion of the cosmos. Some scientists have speculated that if a slight asymmetry in the laws of physics caused antimatter to be more concentrated in certain parts of the universe, it could have led to the formation of entire antimatter clusters. If true, this would mean that there are vast regions of the cosmos that are completely different from what we have observed so far, regions that are fundamentally made of antimatter, with antimatter stars, antimatter black holes, and possibly even antimatter planets that look just like Earth. But if such regions exist, why haven't we found any direct evidence of them? One reason is that antimatter galaxies would behave almost exactly like normal galaxies in every observable way. The light they emit would be identical because antimatter atoms absorb and emit photons just like normal atoms. Their gravitational effects would be the same, meaning they would pull on nearby galaxies and influence cosmic expansion in exactly the same way as normal matter. In other words, if an antimatter galaxy were right next to us, we might not even be able to tell the difference, unless we could observe an actual annihilation event. This brings us to one of the most intriguing possibilities. What if we have already detected antimatter galaxies without realizing it? some unexplained gamma-ray bursts have been observed in deep space, and while most are thought to come from supernovae or neutron-star collisions, a few have unusual properties that defy current explanations. It is possible that at least some of these mysterious high-energy explosions could be the result of matter and antimatter interacting on a cosmic scale. If an antimatter star were to stray too close to a normal matter region, for example, the resulting annihilation could produce an explosion unlike anything we have ever seen before. Some researchers believe that the best way to solve the antimatter galaxy mystery is to look for extremely high-energy cosmic rays that could only be produced by the annihilation of entire antimatter structures. If such cosmic rays were detected in a way that cannot be explained by known astrophysical processes, it would be a strong indication that antimatter galaxies are out there. The alpha magnetic spectrometer aboard the International Space Station has already detected positrons, antimatter electrons, in greater numbers than expected, but so far, there is no definitive proof that these positrons come from antimatter galaxies rather than other cosmic phenomena like pulsars or dark matter interactions. However, even if we do find evidence of antimatter galaxies, it raises another critical question: how many could there be? If only a handful exist in distant cosmic voids, they might be little more than rare anomalies. But if antimatter galaxies are relatively common, it could mean that the universe is structured in a way that we never imagined, with matter and antimatter existing in separate but equal domains. This would completely rewrite our understanding of cosmic evolution and the fate of the universe itself. If the universe contains large-scale matter-antimatter symmetry, it might suggest that the cosmos is even larger than we currently estimate, possibly extending far beyond the observable universe into regions that remain completely hidden from us. It might also hint at unknown physical laws that govern the interactions between matter and antimatter on the grandest scales. Could there be entire antimatter superclusters beyond our reach? Could the balance between matter and antimatter play a role in the ultimate fate of the universe, determining whether it expands forever or eventually collapses in a final annihilation event? The more we search for answers, the more questions arise. If antimatter galaxies exist, they may be one of the most profound and elusive discoveries in the history of science. Their presence would challenge everything we think we know about cosmology and force us to rethink the deepest mysteries of existence. But until we find definitive proof, we are left with speculation, theories, and the ever-present question: could there be an antimatter galaxy somewhere, hiding in the depths of space, waiting for us to find it? If antimatter galaxies do exist, their implications go far beyond theoretical curiosity. They could reshape our entire understanding of the universe's origins and fate. One of the biggest puzzles in physics is why our observable universe is dominated by matter rather than an equal mix of matter and antimatter. The laws of physics suggest that matter and antimatter should have been created in equal amounts during the Big Bang. If that were the case, most of it should have annihilated, leaving behind only energy in the form of radiation. Yet, here we are, living in a universe overwhelmingly made of matter, with no confirmed large-scale antimatter structures. This imbalance is known as the baryon asymmetry problem, and it remains one of the deepest unsolved mysteries in cosmology. The idea that entire antimatter galaxies might exist raises the possibility that the universe did, in fact, create equal amounts of matter and antimatter, but instead of mixing and annihilating, they were somehow separated on a cosmic scale. If this is true, then antimatter galaxies are not just possible but inevitable, existing in vast cosmic regions where they never interact with normal matter. One of the biggest challenges in proving the existence of antimatter galaxies is that they would be almost indistinguishable from normal galaxies. Because antimatter atoms behave exactly like normal atoms in almost every way, forming stars, emitting light, and undergoing nuclear fusion, their galaxies would look identical to ours. This means that even if we had an antimatter galaxy right next to a matter galaxy, we might not notice any difference unless we could detect some kind of interaction between the two. However, one way to test for antimatter galaxies is to search for high-energy cosmic rays that could be the result of matter-antimatter annihilation on a grand scale. If there are border regions where matter and antimatter meet, even in minuscule amounts, they should produce massive bursts of gamma rays. Observatories like NASA's Fermi Gamma Ray Space Telescope have been scanning the cosmos for unexplained gamma ray sources, and while some have been detected, none have definitively pointed to the presence of antimatter galaxies. Another approach is to look for antimatter cosmic rays traveling through space. The Alpha Magnetic Spectrometer, AMS-02, on the International Space Station has been searching for antimatter nuclei, particularly antihelium, which would be a strong indicator of antimatter galaxies. So far, some candidate antihelium particles have been detected, but their origin remains unclear. If these particles turn out to have come from deep space rather than local astrophysical processes, it could be the first real evidence of large-scale antimatter structures. One of the most perplexing possibilities is that antimatter galaxies might not just exist in isolation. They might play a role in the large-scale structure of the universe itself. Some theories suggest that cosmic voids, the vast, empty regions between galaxy clusters, could actually be filled with antimatter galaxies, hidden in plain sight. These voids contain very little normal matter, which means that an antimatter galaxy within one could remain undetected for billions of years simply because there is nothing nearby for it to annihilate. But if antimatter galaxies exist, they also raise new questions about the fundamental laws of physics. For example, how do they remain stable if the universe is expanding and evolving? If there were once regions of matter and antimatter separated by cosmic forces, are they still completely isolated, or could they eventually drift toward each other? If so, could there be a catastrophic future event where antimatter and matter galaxies begin to mix, triggering massive annihilation events across the cosmos? Some scientists have even speculated that antimatter galaxies could be connected to dark matter, another major cosmic mystery. While dark matter is thought to make up about 85% of the universe's total mass, we still don't know what it actually is. If antimatter galaxies exist in isolated regions, could they interact differently with dark matter than normal galaxies? Could dark matter itself be playing a role in keeping matter and antimatter separate on a cosmic scale? Another intriguing possibility is that antimatter galaxies might be so isolated that they exist in an entirely different cosmic domain, one that we may never be able to reach. If the universe is infinite, or if it contains multiple disconnected regions, there could be entire sectors dominated by antimatter, existing in perfect balance with our own matter-dominated region. In this case, the reason we haven't seen antimatter galaxies could simply be that they are too far away, beyond the observable universe. If antimatter galaxies are real, their discovery would revolutionize our understanding of physics and cosmology. It would suggest that the universe is not just a random mix of matter but a structured, organized system where matter and antimatter were separated at the moment of creation. It would mean that our theories about the Big Bang need to be revised and that the laws governing the universe might be even stranger than we imagined. The search for antimatter galaxies is one of the most profound scientific quests of our time, and whether or not they exist, their possibility forces us to confront the biggest questions about reality itself. Are we truly alone in a matter-dominated universe, or is there another side to existence, one filled with antimatter galaxies, waiting to be discovered? If antimatter galaxies exist, they would fundamentally challenge many of our assumptions about the universe's structure and evolution. The idea that entire regions of space could be filled with antimatter instead of matter raises deep questions about the nature of cosmic balance. But how would these antimatter galaxies form in the first place? Did the Big Bang create equal amounts of matter and antimatter that somehow became separated? Or is there an unknown cosmic process that allowed antimatter galaxies to emerge in specific regions while the rest of the universe became matter-dominated? One hypothesis suggests that during the earliest moments of the universe, when temperatures and energy levels were incomprehensibly high, matter and antimatter were created in almost equal amounts. However, due to a slight asymmetry in the laws of physics, possibly caused by an unknown fundamental force, more matter than antimatter survived. This tiny imbalance, potentially as small as one extra matter particle per billion, is what allowed the universe to evolve into the form we see today. But what if instead of a small imbalance, the universe underwent a large-scale separation process? Imagine that, in the chaotic aftermath of the Big Bang, certain regions of space naturally formed with a higher concentration of matter while others formed with a higher concentration of antimatter. These regions, once separated by vast cosmic distances, could have remained isolated from each other for billions of years. If antimatter galaxies formed in these isolated pockets of space, they would look and behave exactly like normal galaxies, creating stars, forming planetary systems, and possibly even supporting life. But this raises another question. If antimatter galaxies exist, could they host antimatter life? Theoretically, antimatter atoms would behave just like normal matter atoms, forming complex molecules and chemical structures. If the conditions were right, there is no reason why antimatter planets couldn't have developed in the same way as Earth, possibly leading to the emergence of antimatter life forms. If this is the case, then somewhere in the universe, there could be civilizations made entirely of antimatter, looking up at their own night skies and wondering if matter galaxies exist. The problem, of course, is that if an antimatter civilization were ever to encounter a matter-based civilization, the results would be catastrophic. Any direct contact between matter and antimatter results in total annihilation, converting all mass into energy. This means that even if we somehow made contact with an antimatter civilization, shaking hands with them would be impossible. It would lead to an immediate, powerful explosion. The possibility of antimatter galaxies also introduces another paradox. If antimatter and matter galaxies formed separately, what would happen at their borders? If matter and antimatter regions of space ever come into contact, we should see large-scale annihilation events producing massive bursts of gamma radiation. However, despite decades of searching, astronomers have yet to find evidence of such large-scale matter-antimatter annihilation zones. This could mean that antimatter galaxies, if they exist, are located in extremely isolated regions of space, far beyond our current observational reach. One theory suggests that if antimatter galaxies exist, they might be found in cosmic voids, enormous empty spaces between galaxy clusters where very little matter exists. These voids, some stretching hundreds of millions of light-years across, could provide a natural barrier that prevents antimatter galaxies from coming into contact with matter galaxies. If this is true, then searching these voids for unusual radiation signatures might be our best chance at discovering an antimatter galaxy. Another approach is to study cosmic rays, high-energy particles that travel through space at nearly the speed of light. If antimatter galaxies exist, they should occasionally produce antimatter cosmic rays, which could be detected by instruments like the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station. In recent years, AMS-02 has detected a few possible antihelium particles, an exciting discovery, since antihelium is extremely rare in our matter-dominated universe. If these particles can be confirmed as originating from deep space rather than from local astrophysical sources, they could be the first direct evidence of an antimatter galaxy. But if we do discover an antimatter galaxy, what would that mean for physics? Would it suggest that our understanding of the universe is fundamentally flawed? One radical idea is that antimatter galaxies could be connected to dark matter, the mysterious, invisible substance that makes up most of the universe's mass. Some theories propose that dark matter could act as a cosmic shield, keeping matter and antimatter galaxies apart, while also influencing the large-scale structure of the universe. If antimatter galaxies exist within dark matter-dominated regions, their interactions with dark matter might provide clues to solving one of the greatest mysteries in physics. The idea of antimatter galaxies also raises profound questions about the fate of the universe. If the cosmos is expanding and antimatter galaxies exist, will they remain forever isolated, or could they eventually drift toward matter-dominated regions? If so, could we be heading toward a future where antimatter and matter galaxies start colliding on a massive scale, leading to cataclysmic annihilation events? Alternatively, some scientists speculate that the existence of antimatter galaxies could suggest the presence of a hidden symmetry in the universe, one that we have yet to fully understand. This symmetry might explain not only why antimatter galaxies exist but also why the laws of physics allow the universe to be structured the way it is. If this is the case, then antimatter galaxies might not be a cosmic accident but an essential part of a deeper, more profound order that governs reality. For now, the search for antimatter galaxies continues, and with each new discovery, we inch closer to answering one of the most fundamental questions about the universe. Is everything we see just one side of the cosmic coin, with a hidden antimatter counterpart lurking in the depths of space? The implications are staggering. If antimatter galaxies do exist, they could change everything we thought we knew about the origins, structure, and fate of the universe itself. The search for antimatter galaxies is not just a theoretical exercise, it's an active scientific endeavor that could redefine our understanding of the cosmos. If such galaxies exist, they would force us to rethink the very fabric of reality. Scientists have spent decades developing methods to detect them, yet the evidence remains elusive. Why is that? If the universe did create equal amounts of matter and antimatter at the beginning, where did all the antimatter go? And if entire galaxies made of antimatter exist, why haven't we definitively found one yet? One of the biggest challenges in detecting antimatter galaxies is that they would appear almost identical to matter galaxies. A spiral galaxy made of antimatter would look just like the Milky Way. Its stars would shine, its planets would orbit, and its black holes would consume matter, or in this case, antimatter, just as they do in the matter-dominated universe. The only way we would be able to tell the difference is through interactions at the boundaries where matter and antimatter might meet. This means that, instead of looking for antimatter galaxies directly, scientists search for evidence of matter-antimatter collisions. The logic is simple. If an antimatter galaxy existed somewhere near the known universe, there should be regions where stray matter particles from our galaxy occasionally drift into it, triggering annihilation events. These events should produce intense gamma-ray bursts, which our telescopes should be able to detect. However, despite extensive observations, no such large-scale gamma-ray signals have been found. But that doesn't necessarily mean antimatter galaxies don't exist. It could mean they are located so far away that their interactions with matter are too rare to detect. It could also mean they are surrounded by vast regions of empty space, cosmic voids that act as natural buffers, preventing matter from ever reaching them. If antimatter galaxies are hidden in these voids, we may only be able to detect them through indirect means, such as studying cosmic rays that travel through the universe. This brings us to a fascinating development: the search for antimatter cosmic rays. The Alpha Magnetic Spectrometer, AMS-02, a particle physics detector mounted on the International Space Station, is specifically designed to look for antimatter signatures. While most cosmic rays that reach Earth are made of normal matter, every once in a while, AMS-02 detects something strange: particles that could be antihelium nuclei. This is significant because antihelium is extremely rare in a universe dominated by matter. If these antihelium particles originated from deep space, they could be the first direct evidence of an antimatter region. However, the challenge lies in confirming their origin. Antimatter can be produced in small amounts by high-energy astrophysical processes, such as collisions between cosmic rays and interstellar gas. This means that before scientists can claim that these antihelium particles came from an antimatter galaxy, they must rule out the possibility that they were created by more common mechanisms. If future detections show that these particles have traveled vast distances from a specific region of space, it could be a groundbreaking discovery. But let's take a step back and consider the implications of finding an antimatter galaxy. If we confirmed its existence, it would mean that the universe has somehow maintained a large-scale balance between matter and antimatter, even if we don't fully understand how. It would suggest that cosmic evolution was not as lopsided as we previously thought, that instead of one side dominating, there might be vast, hidden structures of antimatter spread throughout the cosmos. This discovery could also provide insight into one of the greatest mysteries of physics: the matter-antimatter asymmetry problem. Why does our observable universe seem to be made almost entirely of matter, when physics suggests that matter and antimatter should have been created in equal amounts? Finding an antimatter galaxy could offer a missing piece of this puzzle, showing us that antimatter wasn't entirely annihilated in the early universe. It simply formed in separate regions, where it evolved independently. But then, what would this mean for the fate of the universe? If matter and antimatter galaxies are separated now, will they always remain that way? Or could they eventually drift toward each other over cosmic timescales? If large-scale matter-antimatter collisions occur in the distant future, they could release unimaginable amounts of energy, fundamentally reshaping the structure of the cosmos. Some theories even suggest that antimatter galaxies could be linked to dark matter, the mysterious substance that makes up most of the universe's mass but doesn't interact with light. What if antimatter and matter galaxies are being kept apart by dark matter? What if the distribution of dark matter is the key to understanding why we don't see antimatter galaxies near us? If this is true, then studying the distribution of dark matter could help us locate hidden antimatter regions. This raises another mind-bending possibility. Could there be an entire antimatter sector of the universe? Instead of just a few scattered antimatter galaxies, what if there's an entire antimatter counterpart to our known universe, existing beyond the limits of our observations? Some cosmologists speculate that the universe might be structured in a way where matter-dominated and antimatter-dominated regions exist in a delicate cosmic balance, but separated on a scale so large that they rarely interact. If this is true, it would mean that our picture of the universe is only half complete, that everything we see is just the matter portion of a much larger, more complex reality. For now, the search for antimatter galaxies continues. Scientists are refining their methods, looking for indirect evidence through cosmic rays, gamma-ray observations, and deep space studies. Each new discovery brings us closer to answering one of the most fundamental questions in cosmology. Is the universe truly asymmetric, or is there another side of the cosmic equation waiting to be found? If an antimatter galaxy is out there, its discovery would not only change our understanding of the cosmos, it would challenge everything we thought we knew about the very nature of existence itself. The possibility of an antimatter galaxy existing somewhere in the vast cosmos is not just a question of curiosity. It's a question that could unravel some of the deepest mysteries of physics. If an antimatter galaxy is out there, it means that the early universe somehow allowed large-scale structures of antimatter to form and persist for billions of years without being annihilated. But how could this happen? And if we were to find one, what would it reveal about the nature of our universe? One major factor to consider is the role of cosmic inflation. In the earliest moments of the universe, space expanded at an exponential rate, stretching tiny quantum fluctuations into the large-scale structures we see today. If antimatter galaxies exist, they may have been formed in regions of space that were separated from the matter-dominated regions during inflation. This would mean that matter and antimatter weren't annihilated immediately after the Big Bang because they were physically isolated before they had a chance to interact. But that explanation alone doesn't fully solve the mystery. Even if inflation separated matter and antimatter into different regions, it doesn't explain why we don't see any large-scale interactions between them today. The universe has been expanding for billions of years, and while galaxies are generally moving apart due to cosmic expansion, there should still be occasional encounters between matter and antimatter regions if they exist. And yet, we don't see the expected gamma-ray signatures that such interactions would produce. One possible explanation is that antimatter galaxies, if they exist, might be extremely distant and hidden beyond our observational limits. The observable universe is only a fraction of the entire cosmos. It's possible that antimatter galaxies exist far beyond the edge of what we can currently detect, in regions of the universe that will forever remain inaccessible to us due to the limits imposed by the speed of light. If this is the case, we may never find direct evidence of them, but their existence would still be a fundamental piece of the cosmic puzzle. Another possibility is that antimatter galaxies do exist within the observable universe, but they are surrounded by vast cosmic voids that prevent interactions with normal matter. If an antimatter galaxy were located in one of these voids, it could remain isolated for billions of years, with very few opportunities for stray matter particles to drift into it. This could explain why we haven't detected large-scale annihilation events. However, if we could one day confirm the existence of an antimatter galaxy, it would have profound implications for physics. It would suggest that the laws of physics allow for large-scale separation of matter and antimatter in a way that we don't yet fully understand. It could even hint at unknown symmetries in the universe, hidden principles that dictate the distribution of matter and antimatter on a cosmic scale. One of the most intriguing ideas is that the existence of antimatter galaxies could be linked to the mysterious phenomenon of dark matter. Dark matter is thought to make up about 85% of the universe's mass, yet we don't know what it is. Some theories suggest that dark matter could be a form of antimatter that doesn't interact with regular matter in the way we expect. If antimatter galaxies are surrounded by dark matter halos, they could be shielded from interactions with normal matter, making them even harder to detect. But let's imagine for a moment that we do find an antimatter galaxy. What would it look like? Surprisingly, it would look almost exactly like any other galaxy. The stars within it would shine just like normal stars, because the fundamental physics of antimatter is nearly identical to that of matter. Antimatter atoms would form antimatter molecules, which would form antimatter planets, which would orbit around antimatter stars in much the same way that matter behaves in our own galaxy. This means that if an antimatter civilization existed within an antimatter galaxy, they might not even realize they were made of antimatter. To them, everything would seem normal. Their planets, their stars, and their entire universe would appear to behave just like ours. It would only be if they came into contact with a matter-based civilization that they would realize the difference, though such an encounter would be catastrophic, as matter and antimatter would annihilate upon contact. This raises another mind-blowing question: could there be an entire antimatter counterpart to our universe? Some physicists have proposed that there could be a mirror universe composed entirely of antimatter, existing alongside our own but separated in a way that prevents interaction. This antimatter universe could be just as vast and complex as our own, with its own galaxies, stars, planets, and even intelligent life. If such a universe exists, how would we detect it? One possibility is through subtle gravitational effects. Even though matter and antimatter annihilate upon contact, they both still obey the laws of gravity in the same way. If there were a massive antimatter structure near our universe, its gravitational influence might be detectable. Some researchers have even speculated that the unexplained motions of galaxies, currently attributed to dark matter, could be influenced by an unseen antimatter counterpart pulling on them from another cosmic domain. The search for antimatter galaxies continues, with scientists looking for clues in high-energy cosmic rays, deep space gamma-ray observations, and even theoretical models of cosmic evolution. The detection of even a single antimatter galaxy would revolutionize our understanding of the universe, proving that matter and antimatter can coexist on a cosmic scale. For now, the question remains unanswered. But as our technology improves and our understanding of the cosmos deepens, we may one day find the evidence we need. If an antimatter galaxy is out there, it holds the key to one of the greatest unsolved mysteries in physics: the mystery of why our universe exists the way it does. If an antimatter galaxy exists somewhere in the cosmos, it would challenge one of the most fundamental assumptions in physics: the overwhelming dominance of matter in the observable universe. According to our current understanding, matter and antimatter should have been created in equal amounts during the Big Bang. But if that were the case, they would have annihilated each other, leaving behind only energy. The fact that our universe is overwhelmingly made of matter suggests that something tipped the balance. Some unknown process caused an asymmetry between matter and antimatter. But what if that asymmetry isn't as absolute as we think? What if pockets of antimatter manage to survive, forming entire galaxies hidden somewhere in the depths of space? One of the biggest challenges in finding an antimatter galaxy is that it would look almost identical to a normal galaxy. A spiral galaxy made of antimatter would have the same shape, the same star formation processes, and the same overall structure as a regular spiral galaxy. The laws of physics don't distinguish between matter and antimatter in terms of how they behave in isolation. Antimatter atoms form antimatter molecules, which can create complex structures just like ordinary matter does. So how would we actually detect an antimatter galaxy? The most obvious way would be to look for evidence of matter-antimatter annihilation. When matter and antimatter collide, they annihilate into high-energy gamma rays. If an antimatter galaxy were interacting with the surrounding intergalactic medium, where stray atoms of regular matter might drift into it, we would expect to see a significant amount of gamma-ray emissions coming from its edges. However, despite decades of scanning the skies with gamma-ray telescopes, we have yet to find any compelling evidence of such interactions. This suggests a few possibilities. First, it could mean that if antimatter galaxies exist, they are incredibly isolated, floating in regions of space almost entirely devoid of normal matter. In this scenario, An antimatter galaxy could exist without ever coming into contact with enough matter to produce noticeable gamma rays. This would mean that antimatter galaxies, if they exist, might be surrounded by massive cosmic voids, making them even harder to detect. Another possibility is that antimatter galaxies exist beyond the observable universe. The part of the universe we can see is limited by the speed of light and the age of the cosmos. Since light from the most distant objects takes billions of years to reach us, there could be regions of the universe, far beyond our observational horizon, where antimatter galaxies exist but are simply too far away for us to detect. There's also the intriguing possibility that antimatter galaxies don't exist at all, but instead, the asymmetry between matter and antimatter is total. If that's the case, then the real mystery isn't just whether antimatter galaxies exist, but why there is no large-scale antimatter at all. The imbalance between matter and antimatter is one of the biggest open questions in physics, and solving it could reveal new physics beyond the standard model. One of the most promising approaches to solving this mystery is through the study of cosmic rays. Cosmic rays are high-energy particles that travel through space, and some of them come from deep within the universe. If an antimatter galaxy exists, it should occasionally produce antimatter cosmic rays, such as anti-helium nuclei, that could reach Earth. In recent years, experiments like the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station have been searching for these rare antimatter cosmic rays. If even a few anti-helium atoms are detected, it would be strong evidence that large amounts of antimatter exist somewhere in the universe. But let's take a step back and imagine what it would mean if we actually discovered an antimatter galaxy. The implications would be enormous. It would suggest that the universe is not as matter-dominated as we think and that some regions of space evolved under completely different conditions. It might even hint at new physical laws that allowed for antimatter and matter to be separated on a cosmic scale. Even more mind-bending is the possibility that antimatter galaxies could be home to antimatter life. If antimatter behaves exactly like matter at a fundamental level, then it stands to reason that antimatter stars could have antimatter planets orbiting them. And if conditions were right, those planets could have liquid antimatter water, antimatter atmospheres, and potentially even antimatter life forms. To these hypothetical beings, their universe would feel just as normal as ours does to us. They would be unaware that they are made of antimatter, until they encountered matter, which would annihilate them instantly. This raises an unsettling question: could an antimatter civilization one day come into contact with us? If an antimatter spaceship somehow entered our galaxy, the result would be catastrophic. The moment it made contact with even a small amount of matter, it would explode in a massive burst of gamma radiation. The same would happen if we sent a probe to an antimatter galaxy. It would be destroyed as soon as it touched anything. This makes direct contact between matter and antimatter civilizations virtually impossible. However, communication might still be possible. If an antimatter civilization developed radio technology, they could theoretically send signals that we could detect. Since electromagnetic waves, such as radio signals, are not affected by whether they originate from matter or antimatter, an antimatter civilization's radio transmissions would be indistinguishable from our own. If we ever receive a mysterious signal from deep space, could it be coming from an antimatter galaxy? Another radical idea is that antimatter galaxies could play a role in the mystery of dark matter. Dark matter is an unknown substance that makes up most of the universe's mass but does not emit light or interact with normal matter in any way other than through gravity. Some scientists have proposed that antimatter might interact differently with dark matter than normal matter does. If antimatter galaxies exist, their gravitational interactions could provide new clues about the nature of dark matter and whether it has a preference for one type of matter over the other. At the heart of all these theories is the fundamental mystery of why our universe exists at all. If matter and antimatter were created in equal amounts, they should have annihilated each other completely. The fact that we are here, that galaxies exist, and that the universe is filled with matter suggests that something in the early universe created an imbalance. Understanding that imbalance could be the key to uncovering new physics, perhaps even leading to a unified theory that explains both the existence of matter and the possibility of antimatter galaxies. For now, the search continues. Scientists are using everything from gamma-ray telescopes to particle detectors on Earth and in space to look for signs of antimatter beyond our galaxy. Whether we find an antimatter galaxy or not, the journey to answer this question is pushing the boundaries of our knowledge and bringing us closer to understanding the deepest secrets of the universe. And if an antimatter galaxy is out there, waiting to be discovered, it could change everything we know about reality. The possibility of an antimatter galaxy existing somewhere in the universe forces us to rethink our most fundamental assumptions about physics, cosmology, and even the very nature of existence itself. If such a galaxy exists, it would mean that vast regions of the cosmos evolved under completely different conditions that allowed antimatter to dominate instead of matter. But how would such a thing be possible in the first place? To understand this, we have to explore the origins of the universe itself and the mechanisms that could have separated matter and antimatter on such a large scale. One of the prevailing theories about why our universe is dominated by matter is called baryogenesis. This theory suggests that in the early moments of the Big Bang, some unknown process caused a tiny excess of matter over antimatter. Even if there was only one extra matter particle for every billion matter-antimatter pairs, that would have been enough to leave behind all the matter we see today after the rest annihilated into energy. However, this theory doesn't explain how antimatter galaxies could exist. If baryogenesis was an uneven process, if different regions of space ended up with different amounts of matter and antimatter, then it's possible that some regions of the universe evolved into antimatter-dominated structures. Another potential explanation is cosmic inflation. This is the idea that in the first fraction of a second after the Big Bang, the universe expanded exponentially, stretching out space faster than the speed of light. If some regions of space started with more antimatter than matter, inflation might have separated them far enough that they never came into contact with regular matter. This would have allowed entire antimatter galaxies to form in isolation, undisturbed by the matter-filled universe we know. But here's where things get really weird. If antimatter galaxies do exist, they might be fundamentally undetectable using traditional methods. A galaxy made entirely of antimatter would behave identically to a normal galaxy in every observable way. The way stars shine, the way galaxies rotate, and even the way light bends around them due to gravity would all appear exactly the same. This means that if there are antimatter galaxies out there, we might already be looking at them without realizing it. This is a mind-boggling thought. Right now, when we peer through telescopes at distant galaxies, some of them could be made entirely of antimatter, and we'd have no way of knowing just by looking at them. The only way to truly confirm their existence would be to observe an interaction between matter and antimatter, which would produce the unmistakable signature of high-energy gamma rays. Some scientists have suggested that if antimatter galaxies exist, they should be detectable by looking for unusual cosmic rays. Cosmic rays are high-energy particles that travel through space, and some of them originate from outside our galaxy. If an antimatter galaxy exists, it could occasionally send antimatter particles, like antihelium, toward Earth. Detecting even a single antihelium nucleus would be strong evidence that large amounts of antimatter exist somewhere beyond our galaxy. One of the most ambitious efforts to detect antimatter cosmic rays is the Alpha Magnetic Spectrometer, AMS-02, an experiment mounted on the International Space Station. AMS-02 has been scanning space for signs of antimatter for years, and while it has detected some intriguing signals, nothing conclusive has been found yet. But if even a single antihelium particle is confirmed, it could be a game-changing discovery that would force us to rethink everything we know about the composition of the universe. If an antimatter galaxy is truly out there, what would it be like? Would it have planets? Would it have antimatter life? Theoretically, if antimatter behaves exactly like matter at a fundamental level, then there's no reason an antimatter planet couldn't exist. It could have antimatter water, antimatter clouds, and even antimatter organisms living on it. To them, their world would feel completely normal. The only difference is that if they ever encountered matter, they would annihilate instantly in a burst of pure energy. This raises an incredible possibility. What if an antimatter civilization exists? Imagine an advanced alien species, intelligent and capable of space travel, but made entirely of antimatter. If they tried to visit us, their ships would explode upon contact with our atmosphere. The same would happen if we tried to land on their world. It would be like two different dimensions of reality, forever separated by the fundamental nature of their existence. But here's something even crazier. Could an antimatter galaxy be sending us signals right now? Electromagnetic waves, like radio signals, are not affected by whether they originate from matter or antimatter. That means an antimatter civilization could send radio signals across the cosmos, and we would have no way of knowing they came from an antimatter source. If we ever detect an alien signal, could it be coming from an antimatter civilization trying to communicate with us? Some physicists have even speculated that antimatter galaxies could provide clues about the nature of dark matter, one of the biggest mysteries in the universe. Dark matter makes up most of the universe's mass, yet it doesn't interact with light, making it invisible. If antimatter interacts differently with dark matter than regular matter does, studying an antimatter galaxy could help us unlock the secrets of this invisible force shaping the cosmos. Right now, we don't have definitive proof that antimatter galaxies exist. But the search is far from over. Future space missions, more advanced particle detectors, and better gamma-ray telescopes might one day give us the evidence we need. And if we do find an antimatter galaxy, it will be one of the most groundbreaking discoveries in the history of science. Just imagine what that would mean. The universe, as we know it, would no longer be a place where matter is the only dominant force. It would be a place of duality, where matter and antimatter coexist, separated by vast cosmic distances. It would open up new questions about why the universe took this path, why some regions became filled with matter while others became dominated by antimatter. And it might even reveal new physics beyond anything we currently understand. For now, the mystery remains. But the idea that somewhere, hidden in the vastness of space, an entire galaxy made of antimatter could exist is a reminder of just how little we truly know about the universe. And if an antimatter galaxy is out there, waiting to be discovered, it could rewrite the very fabric of our understanding of reality. If an antimatter galaxy exists somewhere in the cosmos, one of the most profound questions we must ask is, how did it form? Our current understanding of the universe suggests that matter overwhelmingly dominates over antimatter. But if antimatter galaxies exist, it would mean that this dominance is not as universal as we once thought. This leads to a deeper mystery. How could such a vast structure, composed entirely of antimatter, have avoided annihilation with the surrounding matter-filled universe? One possibility is that the separation of matter and antimatter occurred at the very beginning of the universe, in a way that created distinct cosmic regions. In the earliest moments after the Big Bang, the universe was an incredibly hot and dense plasma where matter and antimatter were created in nearly equal amounts. However, under some unknown conditions, these regions could have expanded in such a way that vast pockets of antimatter survived, forming antimatter galaxies completely isolated from matter-dominated regions. If this happened, there could be entire cosmic neighborhoods where antimatter is the norm, just as matter is in our local universe. But why haven't we detected clear evidence of these antimatter-dominated regions? If there were large-scale interactions between matter and antimatter in space, they would produce massive amounts of high-energy gamma radiation, detectable by our most sensitive telescopes. Yet, no such large-scale annihilation events have been observed. This suggests that if antimatter galaxies exist, they must be located extremely far from matter-dominated regions, possibly beyond the observable universe, or they must be so well separated that interactions are extremely rare. This raises another key question: what separates a matter-dominated region from an antimatter-dominated one? Would there be a sort of cosmic boundary where matter and antimatter meet? If such boundaries exist, they could be sites of extreme energy release, where stray particles from one side occasionally cross into the other, causing bursts of annihilation. The detection of unexpected high-energy gamma rays from deep space could be a hint that such a boundary exists somewhere. A crucial part of the search for antimatter galaxies involves looking for cosmic rays that originate from antimatter. If an antimatter galaxy exists, it should naturally produce high-energy cosmic rays, just like a regular galaxy does. The difference is that some of these cosmic rays should be made of antimatter particles, such as antihelium or anticarbon nuclei. Finding even a single confirmed antihelium nucleus would be a groundbreaking discovery, as it would strongly suggest that large amounts of antimatter exist somewhere beyond our own galaxy. The Alpha Magnetic Spectrometer, AMS-02, which is mounted on the International Space Station, has been searching for these elusive antimatter cosmic rays for years. It has detected a few possible antihelium candidates, but none have been confirmed with absolute certainty yet. If a future mission confirms the presence of antihelium or other heavy antimatter elements in cosmic rays, it could be the first direct evidence of an antimatter galaxy sending particles our way. Another intriguing possibility is that antimatter galaxies might be responsible for some of the unexplained astrophysical signals we've observed. For example, certain high-energy gamma-ray bursts and cosmic ray anomalies have been difficult to explain using conventional astrophysics. Some scientists have speculated that these signals could come from matter-antimatter interactions happening on an enormous scale, perhaps at the edges of an antimatter galaxy or within massive antimatter-dominated galaxy clusters. If antimatter galaxies exist, what would their stars and planets be like? In theory, they should be nearly identical to those in a normal galaxy. Antimatter atoms would behave just like their matter counterparts, forming stars through gravitational collapse, undergoing nuclear fusion, and shining just like normal stars. An antimatter planet would have an atmosphere, oceans, and possibly even life, just composed entirely of antimatter instead of matter. To an antimatter being, their world would feel just as solid and natural as ours does to us. But if they ever came into contact with matter, the results would be catastrophic. This brings up another mind-bending thought. What if intelligent life exists in an antimatter galaxy? If an advanced antimatter civilization developed space travel, they might be capable of exploring their own galaxy, just as we dream of exploring ours. But if they ever tried to visit a matter-filled region of the universe, or if we tried to visit them, any physical interaction would cause instant annihilation. Could it be that our universe is filled with intelligent life, yet separated by an insurmountable barrier of fundamental physics? The idea that an antimatter civilization could exist somewhere in the universe is both fascinating and terrifying. If they ever attempted to send probes or signals into our part of space, they would have to do so in a way that avoids direct matter-antimatter contact. This means that the only way we could communicate would be through electromagnetic waves, radio, light, or other forms of radiation that travel through space unaffected by whether they originate from matter or antimatter. In other words, if an antimatter civilization is out there, we might already be receiving their signals without realizing it. Another profound question is how an antimatter galaxy interacts with dark matter. Dark matter is one of the great unsolved mysteries of cosmology, making up most of the mass in the universe despite being invisible and undetectable by traditional means. If dark matter interacts differently with antimatter than it does with regular matter, studying an antimatter galaxy could reveal entirely new physics. Some theories even suggest that antimatter galaxies might be surrounded by their own antimatter-dominated dark matter halos, completely separate from the dark matter that affects regular galaxies. Right now, the search for antimatter galaxies is one of the most exciting and mysterious areas of astrophysics. If we discover one, it will fundamentally change our understanding of the universe, proving that the cosmos is far stranger and more complex than we ever imagined. It would open the door to entirely new questions about how the universe was formed, why matter and antimatter are distributed the way they are, and what other unknown forces might be at play. For now, the idea of an antimatter galaxy remains a tantalizing mystery. But as our technology advances and our ability to observe the universe improves, we may one day find definitive evidence that we are not alone, not just in terms of life, but in terms of the fundamental nature of the cosmos itself. And if that happens, it will be one of the most revolutionary discoveries in the history of science. If we were to confirm the existence of an antimatter galaxy, it would raise one of the biggest questions in cosmology. How many of them are out there? Is this a rare anomaly, or are antimatter galaxies just as common as matter galaxies, separated by vast cosmic distances? The answer could completely reshape our understanding of the universe's large-scale structure. One way to approach this question is through statistical probability. Given the observable universe contains hundreds of billions of galaxies, If even a small fraction of them were antimatter galaxies, there should be detectable signs somewhere. The problem is that antimatter behaves identically to matter in most ways, making it almost impossible to distinguish an antimatter galaxy from a matter one just by looking at its light. We need indirect methods, such as detecting antimatter cosmic rays, observing unexplained gamma-ray bursts, or searching for unusual gravitational effects. There's also the possibility that antimatter galaxies might exist in vast clusters. If the early universe allowed some regions to remain antimatter-dominated while others became matter-dominated, these regions could have formed massive structures on a cosmic scale. Some theoretical models suggest that entire antimatter superclusters could exist, completely separated from the matter-dominated structures we know. If this is the case, they would likely be found at extreme distances, possibly beyond our current observational limits. But how did such massive antimatter structures form in the first place? One hypothesis suggests that certain exotic physics processes in the early universe could have created imbalances in different regions of space. Some theories propose that cosmic inflation, an extremely rapid expansion of the universe in its earliest moments, might have stretched matter and antimatter into separate cosmic bubbles, preventing them from annihilating each other. If this happened, then some of these bubbles could have evolved into antimatter galaxies and clusters, coexisting with matter galaxies but never directly interacting. Another possibility is that fundamental physics itself allows for the creation of separate antimatter-dominated regions. Certain extensions of the standard model of particle physics propose that matter and antimatter interact with gravity in slightly different ways. If this is true, then antimatter galaxies might be distributed in a way that avoids large-scale annihilation simply due to gravitational effects, forming their own isolated cosmic structures. But what if there's another explanation, one that suggests antimatter galaxies aren't just separated by cosmic distance, but by something even more exotic, like alternate dimensions? Some physicists have speculated that antimatter could exist in a parallel universe, connected to our own in ways we don't yet understand. In some versions of string theory and quantum gravity, antimatter might have a unique relationship with hidden spatial dimensions, effectively existing in a parallel but unreachable part of the universe. This idea might sound extreme, but it could explain why we don't see large-scale annihilation events despite the universe being so vast. If antimatter galaxies exist in a sort of parallel space or separate quantum state, they could be just as common as matter galaxies but fundamentally inaccessible to us. Some experiments in quantum mechanics have even suggested that antimatter particles behave slightly differently under certain conditions, hinting at possible connections to hidden physics we don't yet fully understand. If antimatter galaxies exist, another fundamental question arises: could we ever visit one? Right now, this seems impossible. Any spacecraft made of normal matter would be destroyed instantly upon contact with an antimatter galaxy, and vice versa. But if we could find a way to interact with antimatter without direct physical contact, it might open the door to incredible possibilities. One speculative idea is that if we could harness magnetic or gravitational forces to contain antimatter safely, we might be able to send probes to study these galaxies from a distance. Another concept involves using quantum teleportation or other exotic physics to transfer information without requiring physical travel. While these ideas are far beyond our current technology, they aren't entirely impossible within the realm of theoretical physics. More practically, the best way to study antimatter galaxies right now is through astrophysical observations. Future space telescopes equipped with ultra-sensitive gamma-ray detectors, antimatter cosmic ray trackers, and advanced gravitational lensing techniques could help us find clues about these hidden cosmic structures. Missions like the proposed successors to the James Webb Space Telescope or future particle detection experiments in space could provide key insights into the mystery. If an antimatter galaxy is ever confirmed, it won't just change how we see the universe. It will force us to rethink the very foundations of physics. It would challenge our understanding of the Big Bang, cosmic structure formation, and the fundamental nature of matter itself. It might even lead to the discovery of entirely new physical laws, unlocking secrets about the deepest workings of reality. Until then, the search continues. Somewhere, out in the vast darkness of the cosmos, there may be a galaxy filled with stars, planets, and possibly even life, all made of antimatter. And the only thing separating us from them is the fundamental nature of the universe itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.